Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Stepping aside as we jump into Chapter 6 in the Big Ideas Math Integrated Math 1 textbook, we're dealing with exponential functions. Now, I want to let you guys know, this is the last chapter in IM1 that's focused on algebra-based content. That's not to say we don't solve for x and any other things anymore. But after this is a statistics chapter, something on statistics at least, and then the rest is geometry, the rest of the way we do geometry. So until you hit chapter 1 and IM2, this is the last bit here. And this one's a little bit different from the other ones as well. It is on exponential functions. That x, that variable we're talking about, is now in the exponent. You know, you think like 2 to the something power, that something is now x, or at least involves in x. That's where the variable belongs. And it changes the notion of almost everything. And with this section is on, what's the actual title? It's just titled Exponential Functions as a whole. Is that what the chapter's called? Hold on a second. Let me just, this is me kind of not being prepped. Oh, Exponential Functions and Sequences is the name of the chapter. We're going to hit something called Geometric Sequences, which will be somewhat similar to arithmetic sequences, but in an exponential realm. Anyway. 6.1 in exponential functions. I feel like this could be a longer video for a few reasons. Number one, there are 63 problems in total in the problem set. Number two, this is your first introduction to exponential functions. You might have squared a number before, I get that, but just the concept of learning its definition, knowing what a zero exponent is, a negative exponent is, graphing exponential functions, and just having a total reset in mind in algebraic properties regarding what we're going to do here. I might have to spend a little bit of time in the lecture, might have to spend a little time in the problem set. Who knows? Maybe we do, maybe we don't. But jump to the description section down below if you'd like to find anything for this. PDF-wise, I'll have the actual section of 6.1, and I'll have graph paper. I might be providing tall graph paper this time. I have a different kind of axes where they're a lot taller. Exponential functions increase very sharply, so I might not want to just go from negative 10 to 10 on y. I have one that goes from negative 17 to 17, although they're not numbered, which is unfortunate, but I'll show you how to work off of that. So we'll have that. You know, you might have to use a graphing calculator. I'm not sure what other things are involved. And because there's 63 problems in total, you might want to find what specific problems you're looking for. So find the timestamps in the description section down below as well. Without further ado, guys, I'm going to go ahead and get started. We are going to identify and evaluate exponential functions. That does mean if you plug in a number for x, then what comes out, for y, just make sure that you know how to do it. And to identify them is to make sure that you know what it means to be an exponential function versus not. We are going to graph exponential functions. Now, my big thing, and listen, the book's big thing is generally to use tables. You can already see a table right here, and of course I'm going to point to the tables when they're used. Plug in x's, get out y's. For the beginning portions, I might be referencing tables. Afterward, I'm going to work on a tableless version of graphing. Fret not, you've been doing them for linear functions, y equals mx plus b, doing the rise and run and stuff without using a table for a couple chapters now. So it's very possible that you can do them here as well. There's a different mindset. It's more about multiplication now instead of addition. But I want to try and get us into a tableless graphing method so we don't have to use a table each and every time. I don't know if they're going to use transformations yet. I know that in like IM2 and IM3 they may end up doing them. But if they do them in IM1, just kind of be aware. And then solve real-life problems involving exponential functions. We got a word problem bases, and you can see that not everything is linear in real life. Exponential function is the brand new core vocabulary, as well as some old things here. Parent function is just the basic non-transform. It sounds like we are going to transform them then. Parent function, and then independent, dependent variables are your x's and y's. Okay, guys, an exponential function is non-linear, doesn't make a straight line. Straight off the bat, we want to know that. It's a non-linear function of the form y equals ab to the x. Okay, y equals ab to the x. Now, we've seen y equals mx plus b. Let's differentiate these right now. This one has something added to it after as a constant value that is not affected by the x, meaning if x is 0, this still exists. We're going to talk about what happens when x equals 0 in these situations, of course. We're going to have to get used to that. Unless they've already taught you somewhere that that's how that happens. I mean, we'll have to decide if we need to teach you that or if you're supposed to know that already. And m was your slope at the time, and every time x increased by 1, you added another m to things. See, that's how multiplication works. 2 times 7 is 2 plus 2 plus 2 plus 2 plus 2 plus 2. You add that thing that number of times. So every time x increases by 1, you added another slope. That's why we did up this over that. Up this, we just added. This ab to the x power, first of all, this b is nowhere near what this b was. This was a y-intercept. This is not. They're two different things completely. And the a is different from the m as well. And these aren't related in that sort of way. In fact, the b is more closely related to the m, and the a is actually very closely related to the b. We'll talk about that. But every time, as far as order of operations go, understand PEMDAS, if we say that, multiplication is happening right here. A times b to the x. Exponents happen before multiplication. So we raise this to this power first before multiplying by this number. If this had 3 times 2, whatever to some power, I don't do 3 times 2 first, I do 2 to that power first. So just keep that in mind that this is affected by this. So every time x increases by 1, if you know how exponents work, that's another power of b. You multiply another b to your set. It's another times 2 times 2 times 2, not say plus 2 plus 2 plus 2, something like that. Anyway, a can't be 0. Understand if a was 0, it would wipe this whole thing out. That's something natural. B can't be 1, and b has to be greater than 0. So b can be a number between 0 and 1, like a fraction. It can be more than 1. We'll talk about that a little more over time, but imagine if you raised 1 to a power, 1 times 1 times 1 times 1. It doesn't really change anything. And same with no negatives, no 0. 0 doesn't make it exponential, things like that. As the independent variable, x changes by a constant amount. As the independent variable x changes by a constant amount, the dependent variable y is multiplied by a constant factor. That's what I was saying here before, that you are multiplying another portion of your b over and over as opposed to adding, say, an m. Now let's get into their examples. They're going to first start by identifying functions, and we can talk about what it means there. So as x increases by a constant amount, we need a constant product of y. Does this table represent an exponential function on a? X is adding 1 to each thing here. Y has it is a difference of 2 and 8 and 36, but we're not really looking for differences anymore. We're looking for ratios. It has a ratio for 2 times 2 is 4, 4 times 3 is 12, 12 times 4 is 48. That is not constant. We need a constant ratio, constant multiplier. In this case, it's not. So you can also check this in different ways. You can do 4 divided by 2 to figure that out, 12 divided by 4 to figure that out, 48 divided by 12 to figure it out. But the point is, this is not constant. Therefore, this is not exponential. It increases, and it increases rapidly, but exponential functions very specifically have a constant common ratio. As x increases by 1 here constantly, you can see on this one, you're multiplying by 2 each time. This is an exponential function by nature, and this is what we're going to be seeing in our own tables, from equations to make graphs and all that. They show you once again that if you divide one number by the one before it, you get the same value out, this 2 as well. And that'll probably be important when it's not so easy to figure out what you're multiplying by. We have to make sure to keep that in mind when we do those later. Let's evaluate some exponential functions. Let's do some substitution. Let's see what they have you practice and learn to do. It seems like there are things you're going to have known beforehand, so I'll talk about them very briefly, and then I'll move forward. So negative 2 times 5 to the x when x equals 3. This is where order of operations takes hold. You substitute 3 for x, of course. They could even use function notation if they wanted, but they didn't. And you got to do 5 cubed first. You don't do negative 2 times 5 first. That would give you a different result and an incorrect result. You can try it in your calculator even. Literally, negative 2 in parentheses 5 cubed. I might even do it with you here. 5 cubed is 5 times 5 times 5, 125. Negative 2 times 125 is negative 250. Let's go to the calculator here and show you that exactly that thing. Negative 2 times, calculator's not working again. Reset, please. Let's try it again. Negative 2 times 5 cubed. Looks like that, right? Negative 250. Now, that's the same as what you saw before. What if I did negative 2 times 5, which is negative 10? What if I did negative 10 cubed? Like this. Oops. I'm wrapping it around parentheses to emphasize the fact that it is negative 10 that I'm cubing. It's negative 1,000. That's a different answer, and that's the wrong answer. Right? Our answer is supposed to be negative 250. Order of operations, PEMDAS, we do the exponent first. This one's raised to a negative exponent. Now that is a 0.5, which is also 1/2. I might make mention of that in a bit. But they seem to go straight from this step to this step without blinking. It's like you're going, wait a second, how did that happen? Do I have to use a calculator for that? You don't. You don't. So here's where it seems like we're going to have to know something about something here, okay? Raising to a negative exponent is the same as raising it to a positive exponent if you place it in the denominator, if it turns into division. When you see 3 times 0.5 to the negative second power, that's the same as 3 times 1 over 0.5 to the positive second power. Now, you might not know what 0.5 squared is, so there are different ways of going about that. 0.5 is also 1/2. You can flip the 1/2 into 2 when you do that. So there are a lot of different ways that we can talk about what that thing is. But 0.5 squared is 0.25, and 3 over 0.25, I'm going to let you know right now, is 3 divided by 1/4, which is 3 times 4, which is 12. So there are a lot of different things around that unfortunately I haven't ever done any videos or used the textbook in any big ideas math portions before IM1. So I suppose it's expected that you know how negative exponents work, and I guess it's a good time to talk about how the zero exponent works. Any non-zero value to the 0 power is 1. It's not 0. So this is obviously, they're going to use some tables, and we're going to emphasize this fact a little bit more in a bit. But I need to bring these up now as if they've probably been taught before, and don't be surprised when they don't actually sit down and teach it, that they do it again without blinking and go straight to the next thing. This is a big surprise that they go straight from here to here for me. Like I said, this will be a slower video as an overall. I want to make sure all these things are covered greatly, especially when I start graphing, and I start graphing without a table, and it's a little whip fast. At some point, I speed up. Here's the thing. This is the only section that we have in the chapter on graphing exponential functions. Either I speed up here or I don't. And that's my goal. Ultimately, that's my goal. Graphing exponential functions. Speaking of which, we're going to jump straight into it right now, okay? The graph of a function y equals ab to the x is a vertical stretch or shrink by a factor of the absolute value of a of the graph of the parent function y equals b to the x. Okay, so a parent function, normally they'd put a number here if I put like the number 2, for example. If there is some sort of number right here, this is the one that's being raised to the power. You don't see any number in front of here, and because a multiplies by the number there, a number that's visibly invisible, a number that's invisible to us means it's calculated as being a 1. This is being multiplied by 1. So a being 1 means there's no transformation on that portion of it. Now, they mentioned vertical stretch or shrink. I think we're pretty familiar, at least at the time, with the notion of multiplying something by your function, which affects your y values, ends up being a vertical stretch or shrink. Now, they did say absolute value of a as to not influence what happens when a is negative, because a is negative doesn't determine whether you stretch or shrink. It determines whether you reflect over the x-axis or not. And of course, we're going to talk about that. But if a is 3 or negative 3, either way, it's still vertically stretched by a factor of 3. Now, eventually, you're going to hear me do some different things with a as an overall, meaning it's going to be part of a reference point. It's kind of part of my placement of everything. It's kind of like the y-intercept of the slope-intercept form world in a way. But you're going to hear me do some different things with it. But the bottom line, the bigger the a is, the more your graph is going to be vertically stretched. The smaller a is, the more it's going to be vertically compressed. Now, if a is negative, the graph is reflected in the x-axis. It's flipped over. So you can see this blue graph, a is a positive number. It's a is greater than 0. 2, 1/2, 17, which is massive, or 1. It's going to be an upwards facing graph. And by the way, guys, this is what exponential functions look like. They're nonlinear. They're not parabolic either, right? It's not a U shape, but it is curvy. We're going to talk about obviously why that is when we get more into the table features, plot the points, things like that. When a is negative, suddenly it's a downward facing graph. It makes it a negative function, It's not always below the x-axis. If we talk transformations, we'll see if those arise. But you can see there's that curvature downward underneath for now at the x-axis. Now, there are different things that can affect b here, there are different things that affect your graph when b changes. You'll notice here they mentioned b is greater than 1. b is that value that's raised to the power, like I said, 2 to the x power, for example. Every time x increases by 1, that's another 2 multiplied to something. What happens when you multiply something by 2? It gets bigger. I mean bigger positive, bigger negative, like negative 50 to negative 100. It gets bigger in its own direction, right? So it grows. It's exponential growth when b is more than 1. Remember, b can't be 1. Multiplying by 1 doesn't change your value. Multiplying by 1.1 will make it grow. Not as much as 2, not as much as 5, but it will grow. It's a vertical stretch. I shouldn't be talking about vertical stretches, things like that. This is a growth factor. When b is between 0 and 1, remember it can't be 1 and it can't be 0, it can't be negative. So 1/2, 2/3, 4/5, like things like that. When b is between 0 and 1, what happens when you multiply a number by 1/2? And this is going to be kind of tricky because I forget how often we've talked about this, but multiplying by 1/2 is the same as dividing by 2. You take half of what it was, literally. So it gets smaller. Smaller positive, smaller negative. So as x increases by 1 in this set, that's another 1/2 that's multiplied to your value. What's, 12 times 1/2? That's 6. What's 6 times 1/2? That's 3. What's 3 times 1/2? 3 halves, 1.5, whatever it is. We'll talk about those, but it's shrinking in a way. We're going to say the word decay eventually. It's decay. We're looking at the 4 different versions of graphs we're going to have. Positive exponential growth, negative exponential growth, positive exponential decay, and negative exponential decay. Now, it's worth mentioning, and I believe it's talking about it right here. It says it approaches the x-axis but never intersects it. And that's true, at least with respect to this function non-transformed. No vertical shifts or anything like that. It's getting closer and closer to 0. See what happens if you take half of a half of a half of a half, right? You get a half, think about pizza slices that you're cutting up, right? I got a pizza, I cut it into half of a half, that's a quarter, and then an eighth, and then a 16th, and then 1/32 and 1/64, and it's shrinking and shrinking, and those pizza slices are getting super small, right? You get 1/1,billion. What is 1/1,billion? What number is it really close to? Really close to 0, right? Is it 0? No. Does it ever become negative? If I keep taking half of a number, does it ever turn to 0? Does it ever turn negative? No. The y values that we get out of plugging in values for x, no matter how large or how small, in this case if I make it negative, this graph gets closer and closer to the x-axis, y equals 0. Remember, that's a horizontal line, y equals 0, but never touches it. Now, I don't know, based on the vocab, they never use this word, and I'm going to be using it over and over. I'm probably even going to be drawing them, but this is approaching what is known as an asymptote. Normally, we draw a dotted line to represent it like this. That's not the same thing as, well, it kind of seems like the same thing, like with inequalities, like it's not a solution, that kind of thing. But it's a dotted line that we draw, and I will be drawing it. It's a dotted line that we draw to feature points that your graph never touches nor crosses. There's a horizontal asymptote on the x-axis for non-transformed graphs such as these ones, at least non-translated graphs such as these ones, as to indicate that our points never actually touch this x-axis. Our y value never actually becomes 0, and this will be reflected in our domain and range. I can see we're going to be talking about domain and range here in a bit. So I wanted to really slow down and talk about that, and I'm going to now move forward and get to more of the graphing. Let's do some graphs. Let's graph f of x equals, and notice that's the same as y, f of x equals 4 times 2 to the x power. Remember, 4 times 2 does not simplify here because 2 has to raise to the x power first. Compare the graph to the graph of the parent function. Describe the domain and range of f. Remember that the parent function, by the way, is without this 4 in place, meaning if it was a 1. So this is our parent function right here. 2 to the x power, 1 times 2 to the x power. So they're going to use a table. They're going to plug in some values, -2 to 2, but I'm going to start to get into the process of how this pattern can work without a table by introducing over and over through their table examples what they're doing. So let's look at this here. First of all, you notice this 4 here, and you notice this 4 here. I don't know is it a coincidence it's there? Not entirely. As long as there's no vertical translation on this thing, remember when x is 0, 2 to the 0 power is 1. Well, 4 times 2 to the 0 power is 4 times 1, which is 4. What happens when x is 0 on these problems? B to the 0 becomes 1. So what does a times b to the 0 become? A times 1, which is a. What's the point of that? Your y value is a when x equals 0. Your x equals 0 value is your y-intercept. 4 is our y-intercept. This a value on non-translated functions, the a value is your y-intercept. That's going to be an important feature in what we do. Remember when y equals mx plus b? B was the y-intercept because when x equals 0, blah, blah, blah. That's the same thing here that we want to talk about. It's the y-intercept. So there's a point on the graph. Boom. 0, 4. Now x increases by 1. You can do 4 times 2 to the first power, which is 4 times 2, which is 8. And then 4 times 2 squared is 4 times 4, which is 16. But if you also notice, these have a constant ratio of 2. Where have we seen 2 before? Oh, right here. Right here. So 2 is the growth factor, and sometimes a decay factor. As x increases by 1, that's what's happening here. That means over here we can do times 2 to get 4 and times 2 to get 2. from those numbers. So if you have to work backwards, if you actually did start from the intercept here, if we're multiplying by 2 going one direction, I guess that would mean we're dividing by 2 going the other direction. There are other ways of saying divided by 2 that I'm going to talk about later, such as multiplying by a fraction. We're going to have to get into some of those, especially if we have trouble calculating what those are, or if they have fractions to begin with. But there it is. These are points on the graph, and when you plot all these points right here, you can see they are non-linear. We don't use a ruler, and there are points that exist in between. It is a continuous function. We're not really getting into what's the in-between, but try and do the smoothest curve as you can as possible, keeping in mind that this will not crash through the x-axis. This thing will become divided by 2, divided by 2, divided by 2, and get closer and closer to 0. It may look like it's on the x-axis here. We can just state right now that it's not. If I drew an asymptote, that's my way of saying that it's not, as well as I don't go through the x-axis itself. Now, the black one is g of x equals 2 to the x power. That's if you, again, let me write this. The g of x equals 1 times 2 to the x power. If we went by my mantra that I stated before, because they did not use a table on this one, the a value is 1. That means it's also your y-intercept. Notice right here, this value, these are going by 2's. Half of 2 is 1, so this is your y-intercept here. These are going by 2's as well. I don't know if you'd really notice by the points, but that means this is 1 here. This is 1, 2. This is 2, 4. This is 3, 8, and 4, 16. What's happening to our g of x values every time x increases by 1 on these things here? At 0, we have 1. At 1, we have 2. At 2, we have 4. At 3, we had 8. At 4, we had 16. What's happening each time here? Multiplying by 2. Does that look familiar? It should. It's the same growth factor as this growth factor was at the time. So we're still multiplying by 2, but from a smaller amount. That's what makes this thing be a vertical stretch, right? This is 4 times larger at every y value compared to the others. This was 1, this is 4, 4 times bigger. This was 2, this is 8, 4 times bigger. This was 4, this is 16, 4 times bigger. So it's vertically stretched by a factor of 4. Not that I tend to look at it that way. I kind of find a reference point like this, and then I do my doubling effect. But here you can see the doubling effect happen as well. And of course, this way you divide by 2. This must be 1/2 and 1/4 and things like that, which are a quarter of these ones. But that's the parent function, which we'll get to graphing, I suppose, quite a bit. They're going to probably say, compare the graph of this to the graph of that. And then describe the domain and range. We haven't gotten to that yet, so let's get into that now. Where do they say it? Vertical stretch by a factor of 4. The y-intercept is 4. Is above the y-intercept of the graph of g1. Man, that's a lot of things to write. I don't know how much I'm going to state there. From the graph of f, you can see the domain is all real numbers. I guess that's us understanding what happens here, guys. I can still plug in any value for x in an exponential function. I can plug in positives, 0, negatives, fractions, positive infinity, negative infinity, you know, as big or small as I want, and there will be values for it. No matter how sharp it goes, no matter how flat it goes, there will be y values for any x. So the domain, in this case, as I'll do the symbol, is still all real numbers. The range is a little bit different, though. This is unlike linear functions. This does not, it goes up forever in this case, but it does not go down forever. It only goes down as low as the x-axis, and even then it doesn't actually hit it. So when we describe our y values here, we have to state how low it actually gets. It doesn't actually truly even get a y value of 0 ever. It stays above it. Our y values are always positive. And that's how we state that. We say our y's will be greater than 0. They state the same thing here. The range is y is greater than 0. Get used to your ranges being limited on exponential functions, being greater than or less than whatever your asymptote is. And if we're not transforming our thing by translation, it's going to be above or below 0. Case in point, we are going to have some negative graphs here. So we do have f of x equals negative 1/2 to the x power. This is the new one in red. The negative is representing your a value. Your a in this case is -1. -1 times 1/2 to the x power. Remember, this is y equals a b to the x. What did I state before about a being on your graph? The y-intercept? Oh yeah, look at that. This is -1 here when x equals 0. So it's once again your y-intercept. Now again, if things are going to change when we do transformations, then so be it. We are still going to be doing things in relation to our asymptote. But for now, all intents and purposes, it's your y-intercept. When x equals 0, this part goes away. Now what's happening here is we're multiplying by 1/2. And multiplying by 1/2, like I said, is the same as dividing by 2. It's a form of decay. Your numbers get smaller. Even in negative realm, it's getting closer to 0, right? Smaller. So -1 times 1/2 is -1/2. Times 1/2 is -1/4. You just multiply straight across. 1 times 1 is 1, 2 times 2 is 4, things like that. And then we divide by 1/2 going the other way, right? But there's a much easier way of saying dividing by 1/2. Multiply by its reciprocal, multiplying by 2. So multiply by 2. If we're taking half of something one way, then we're doubling something the other way, because obviously half of -4 is -2, half of -2 is -1. Take half one direction, double the other direction. That's the idea. So these are points on a graph that we can plot as well. The way I'm generally going to try and do it in a tableless manner is starting from my y-intercept value, or whatever reference point I have. Every time x increases by 1, take half of your value. Half of -1 is -1/2. Half of -1/2 is -1/4. And then -1/8 and -16th if you keep going. The point being it never hits 0 for y. It still never hits 0 for y. And we have a doubling effect going this way. When x decreases by 1, you double it. When x decreases by 1, you double it. So there's a lot going on with that. There is an asymptote there still at y equals 0. Horizontal asymptote has to say we never actually hit it. Now the original parent function is if a was a positive 1, which is just truly stating this was only a reflection of what this was. If a is a positive 1 here, then its y-intercept is 1. And then half of 1 is 1/2, half of a half is a quarter. Same thing as the other side of this. This is positive exponential decay on the parent function, negative exponential decay on the transformed function, on our function that we have. It's weird to say, though, negative decay, and you're like, but Mr. Robinson, it's going up. Yeah, there's kind of a double negative going on there, right? Negative decay. Negative is underneath the asymptote. Decay is getting closer to 0. So it'll go up, but it's losing negative value. It's losing negative value. That's what makes it negative decay. This is positive decay. And this was positive growth. Remember, negative growth would look like this one right here. If this was negative and then 2 to the x power, like that, it would be something like that. Like this one. This one here would be negative growth. I'm not going to graph it. Well, rough sketch. It's going to look like that. The y-intercept would be 0. I guess I'm going to graph it. Y-intercept would be 0, -2, and you'd multiply by 4 every time x increased by 1. Okay, lots so far. Like I said, probably one of the longer videos to be here. We are doing transformations. Now, these are things I'm even doing as late as IM3. So the good news is for you, this isn't the only time you're going to hear about exponential functions in integrated math stuff. I think you'll hear about it in IM1, 2, and 3. So they keep getting revisited, which is nice. But there's a lot to take into here based on what we did in the past. To graph a function of the form y equals ab to the x minus h power plus k, begin by graphing y equals ab to the x. I might not necessarily do what they do here, but they are describing transformations. That's the big thing. If you remember the whole f of x minus h plus k stuff, a times f of x minus h plus k stuff, this kind of stuff right here, where our g of x is a transformation of our f of x stuff, that's what's happening here. The x minus h is in respect to horizontal translations, and it's opposite of what you see inside here. X minus h, it's up, I'm not going to get deep into that because it's something we would have already learned at a previous point, but that's horizontal translations. Plus k is vertical translations, things that happen after the fact there. And both of them have their little things. Because they're probably going to have us graph parent functions to begin with, I understand, well, actually, I don't have to do that. I'm going to say what they do. I'm going to say what I do, okay? So I do something slightly different here. They say graph the parent function first and then apply transformations. And I get it. I understand why they talk about it, and actually it's a good lead-in into how I do what I do. So right here they say graph y equals 4 times 2 to the x minus 3 power plus 2, describe the domain and range. By the way, did we look at domain and range for the last? We didn't. This range I wanted to state was y is less than 0, while domain is still all real numbers. It's less than 0 because we're underneath right there. So let's get into this one right here, and this will change our range because there is a vertical translation on this thing. But they do start by graphing y equals 4 times 2 to the x power. So a reminder on how that will work without use of a table is 4 is your y-intercept in this case. Boom. 2 is what we multiply 4 by when we want to increase x by 1. X becomes 1 bigger because these are going by 2s. X is 1 bigger. Now 4 times 2 is 8. X is 1 bigger. 8 times 2 is 16. You can see why I'm going to need taller graph axes as a result of this, so I am going to use that taller graph paper as a whole. Dividing by 2, 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2 is 1/2, and this is what happens every time you decrease x by 1. You're dividing another 2. That's how negative exponents work. So those are some of the points on the graph. Now they do a translation of this stuff. They take our points and they move them over. They moved everything 3 units right. Remember, these go by 2s. They moved everything 3 units right and 2 units up. That's how the h and k works. Remember, h is an opposite effect. So this goes 1, 2, 3 units to the right, and then 1, 2 units up. And that's the new point there that represents what's going to be, for me, my reference point on these graphs. Everything else goes obviously 3 right and 2 up, 1, 2, 3 to the right and 1, 2 up, or you can kind of count how far up and over. I probably wouldn't do that because it's not a slope. But they go 3 units right, 2 units up like that, and then boom, we get the points on the graph like that. It's a little interesting. Let me kind of show you what I'm going to be doing based off of this, okay? Remember what I stated about the whole you can never become 0 for y. That's assuming non-vertical translations. Maybe you can, maybe you can't once we translate. But if you can never become 0 for y, that means that this graph, even with the horizontal translation, this portion here, I could never plug in a number for x that'll get me a y value of 0, ever, period. Domain of all real numbers, I'll never hit 0 for y. What if I add 2 to all those numbers? What if I make all those numbers 2 bigger? Not only will I never hit 0 for y anymore, now I'll never hit 2 for y. Imagine that you do 4 times 2 to the negative 1 billionth power. That's a number really close to 0, but still above 0. Then you add 2 to it. It's a number that's really close to 2, but still above 2. What's the point I'm making? Look at this blue graph. Notice how it's flattening out at this value. What value is that? That's y equals 2. Notice again, these go by 2s. This has a horizontal asymptote. This is what they're not stating that I really wish they did. This is a horizontal asymptote of y equals 2. I'm saying that word asymptote. You might not know what I'm actually saying. Here's the spelling. I believe it's Greek. Asymptote. Asymptote. The asymptote is y equals 2. You can Google it. You can search it. What we're stating is we're never going to hit 2 for y because everything's going to be 2 bigger than what it was before that could never hit 0. Why am I stressing this? Well, because your graph is going to cater to it, but also this is, to me, my new x-axis. I'm shifting everything up too, and that's how I'm going to begin my graphs. I'm going to begin by drawing my horizontal asymptote, especially on these shifted ones. And this thing right here, again, focus on the blue, don't focus on the black, please. I wish there was a way to hide it, but focus on the blue. On this horizontal asymptote, I love to plot the point that is 4 units above the asymptote. It might not be the y-intercept anymore, though, because there's also a horizontal translation. If I go 4 up from here, 2, 4, you can notice there's no point right there because we're also shifted 3 to the right. So that's what that minus 3 is. I'm going to shift 3 to the right, and boom, this is my reference point right here. It's 4 up from the asymptote, and it's 3 units to the right. Now, remember, it is 4 up from the asymptote, right? That's its distance. This is 4 up from it. The next point when x increases by 1 will be 2 times higher up from it. This will be 8 up from the asymptote, not from whatever the y, this y value is 6. This isn't 12. This is 8 up from the asymptote. The next one when x increases by 1 is 16 up from, well, no, I guess that's not the right place. Right here. It's 16 up from the asymptote right here. 16 up from there. You keep doubling your distances. On the other side, you keep dividing by 2. So this is 2 up from the asymptote right here, things like that. It would keep dividing. So everything for me has to do with distance from the asymptote. That's what I'm going to be doing. Now, domain is still all real numbers. That will not change unless it's a word problem basis. Maybe we'll change it. The range is y is greater than 2. Once again, as I stated, you'll never hit 2. You'll never hit anything below it because the 2 that's being added there. It's a translation of a graph that before could never hit 0. So that's what we're doing. Okay, comparing exponential functions. An exponential function, g, models a relationship in which the dependent variable is multiplied by 1.5 for every 1 unit the independent variable x increases. So they're giving us a situation here. They're describing it. They're saying if something multiplies by 1.5 each time, we're going to make, let's see, do they let us make the equation? Do they? Okay, they don't seem to let us make the equation. Maybe I have to get into that in a bit. But that's the thing, that's going to be the base of your exponential function. It says graph g when g of 0 equals 4. Okay, so they're giving us the information for a table. I'm probably going to be working off equations. I know I'm going a little bit opposite of the book, but I'm probably going to go off equations so we can do things without need of a table necessarily. 1.5, maybe you want a table because the numbers are a little weird. We can at least use a calculator. But what's happening here? G of 0 equals 4 means there's a point that's 0, 4. We understand in a non-translated y equals ab to the x graph, y equals ab to the x, that the a value is your y-intercept. So this is y equals 4 times some b value raised to the x power. The b value is what we're multiplying by each time x increases by 1. That's 1.5. This ends up being our function, g of x. This ends up being our function for this particular graph, which means I could use this to make a graph without use of a table, even if I have to use a calculator. But using their table, let's see how this works out. Y-intercept is 4, 0, 4, and then we multiply by 1.5 each time x increases by 1. So times 1.5 here, times 1.5 here, and just trust that these numbers are times 1.5, and then divided by 1.5. I don't know if that's rounded or not, but just trust that that's the notion of it. So the original parent function f would have just been 1.5 to the x power. And this is, well, actually, no, I take it back. Hold on a second. What are they doing here? What's f? What's f? What's f? Compare f from example 3. Oh, what's example 3? Example 3 is 4 times 2 to the x power. So what we're looking at in comparison is both of these. There's 4 times 2 to the x power versus 4 times 1.5 to the x power. Okay, let's actually color code these based off the graphs that you see. G is in blue and the other one's in black. So what's the difference here is obviously the 1.5 versus the 2, but what happens on the graphs? Just because something's a 2, does that mean everything will be taller? Not everything. The y-intercept is the same. They're both 4. It's what happens after 4 that completely changes. Every time x increases by 1, we now double it. 4 times 2 is 8. 8 times 2 is 16. But here you got to do 4 times 1.5, and that's 6. 6 times 1.5 is 9. 9 times 1.5 is 13.5. There's less exponential growth on the 1.5 effect than there is on the 2 effect. And same on the other side. Here we divide by 1.5. That's a bigger number than dividing by 2. 4 divided by 2 is 2. 4 divided by 1.5 is about 2.7. So you can see there's a lessening effect there, but you can also see that they both approach 0, ultimately. Approach, not become. They approach 0 here. They're both positive exponential functions, with exponential growth, I should say. They both have positive exponential growth. And that's it. They do say compare. What do they say? Compare g to the function f from example 3 over the interval x equals 0 to x equals 2. So I kind of stated that f is taller in those cases there. Let's see how they say it. They say both functions have the same value when x is 0, but the value of f is greater than g over the rest of the interval. Yeah, so when we go from 0 to 2, f increases more sharply than g does because of its growth factor. But they do have the same y-intercept. They have the same y-intercept. Okay, real life problems. Probably our last page of our lecture, and this is, like I stated, the largest lecture, probably the largest video we're going to have. For an exponential, at least so far, for an exponential function of the form y equals ab to the x, the y values change by a factor of b as x increases by 1. Touche. Times 5, etc. You can use this to write, I did it one problem too quickly. But you can use this to write an exponential function here. So their exponential function is y equals 2 times 5 to the x power. Do we understand it at this point now, though? This is the y-intercept, which represents a. Boom, y-intercept there. This is your growth factor, which represents b. So this is going to be the b value right there. This is how these work. This is also how we can use these to make graphs without use of a table. Modeling with mathematics. The graph represents a bacterial population y after x days, and now just reproduces. Ugh, bacteria. The graph did write an exponential function that represents the population. So if we notice here, they made a table out of it to be sure, but if you notice here, every time we have a y-intercept of 3, and every time x increases by 1, you're doing 4 times larger than the previous number. 3 times 4 is 12, 12 times 4 is 48, etc., etc. So 3 being the y-intercept, 4 being the growth factor are the two values that we're going to write into our equation. This will be y equals 3 times 4 to the x power. We're getting it. We're getting in that notion here. They then say part B, find the population after 5 days. So here's part A, the equation with the model. Find it after 5 days. X represents the number of days, so we substitute 5 for x. Now we're also going to use units in our final answer. But 4 to the 5th power, it's not the same as 4 times 5. And you might want to use a calculator for it. But 4 times 4 times 4 times 4 times 4 is what we're doing there. It's 1,024 times 3 after that. 3,072. There are 3,072 bacteria after 5 days. Ooh. And then it only does times 4 on the next day, right? There are about 12,000 some bacteria after that. So there it is. You can look at the graph here, that constant growth. Now you can tell here, I don't know if they mention it. They don't really. But if you notice here, domain here might not necessarily be all real numbers, meaning x might not have negative days involved this time. That's possible. It's very possible that your domain is restricted when it comes to word problems, real life applications. Otherwise, you can plug in any number for x. It just might not represent something with respect to the model for the situation on these. Okay, that's the end of the lecture portion. Almost 40 minutes worth. Have we had one quite that long? I can't remember. Very long one here, and we still have this 1 through 4 to start with before we do the official numbers 5 through 63. Yeah, 5 through 63 set with graphs and all. So here we go. Vocabulary and core concept check. Number 1, open-ended. Sketch an increasing exponential function whose graph has a y-intercept of 2. So for that, because the y-intercept is 2, I'm assuming my asymptote is on the x-axis here. Personally, I'm just going to make that assumption on this thing. We are going to have a y-intercept here of 0, 2. For it to increase, that means it's going to have exponential growth, and it's going to be taking off in this direction here. It's going to be decreasing closer and closer to the x-axis, but it never actually hits it. Now, I'm going to indicate those, by the way, guys, with a little half arrow. I don't know if that's an actual mathematical thing to do versus a full arrow, but my half arrow, if you notice, a half arrow is kind of an indicator of I go down more and more, and it continues forever, but it never actually crosses that value. So that's how I'm going to go about it. That's number 1. Number 2, why is a the y-intercept of the graph of the function y equals ab to the x? Well, I'm glad they're asking that. This is a question I would absolutely assign to my students if I saw it, which I do see it now. But in this kind of question, it's the value of a y-intercept is the value of y when x equals 0. A y-intercept is the value of y when x equals 0. In this case, y equals a times b to the 0 power. B to the 0 power is 1. And that's a times 1 equals a. So there is a point on the graph that is 0, comma a. And if it's the y-intercept's value of y when x equals 0, then 0, comma a is the y-intercept. So that's it. That's why. And I don't think they mentioned that. I don't know if I'm being forgetful here. I don't know if they actually mentioned the y-intercept thing. I did. I've been mentioning it over and over. I'm not going to stop. But I don't know if they actually made that mention. They kind of used tables the entire time. They got into that feature set writing equations, but let's hit that home. I think it's something, because now they've introduced it, that's something I'm going to keep using. I would have anyway, but now I get to confidently do it. Number 3, writing. By the way, my neck's bothering me. I'm going to do a couple of these sometimes. I have 63 problems set to go here. Number 3 on writing, compare the graph of y equals 2 times 5 to the x with the graph of y equals 5 to the x. Well, this is one of those things where we're just talking about a vertical stretch. It's literally something that's affecting your function. Remember, the function is the exponential portion, which is what 5 is being raised to. Something after that is happening, right? The graph of g, or the graph of, well, the graph is a transformation, is a vertical stretch by a factor of 2. It's going to be twice as tall for every x value. The y's are going to be doubled for every x value compared to the original one there. You could also state, I mean, we could state other things. For me personally, what I'm going to do is state, hey, this is a y-intercept of 1. This is a y-intercept of 2. That's going to be the big difference for me, but my description will have to be this. Number 4, which one doesn't belong? Which equation does not belong with the other 3? Explain your reasoning. What I'm looking at here, and this might not come right off the bat for you right now, but you might say, oh, this one's different from the other 3 because this is just a 3 and these ones have parentheses or something like that. That's not exactly what's happening here. This is also y equals 1 times 3 to the x power. So it has some y-intercept and it has some growth value there. This is a 4, which is different from 3s. You might say, oh, this is a 4 and these are 3s. That's not the thing either. These are actually the same. I got to just point them out right now. This one's different. The difference in this one is that the 3 is negative. And here's the thing. We cannot have a negative b value. I can't get deep into the y as of right now, but the bottom line is it's not an exponential function. In an exponential function, b must be greater than 1 or between 0 and 1. That's it. If it's 0, 1, or negative, it's not exponential. Now, there's a difference. There's a difference, and I'll find one in a moment. I don't see one yet. There's a difference between f of x equals negative 3 to the x power like that, and f of x equals negative 3 to the x power like this. This one is negative 1 times 3 to the x power. That's allowed. That's okay. That would be the equivalent of putting the negative right there. That's okay. This one is not. This is a b value of 3. This is a b value of negative 3. No good on that one. Yes, good on that one. Okay. And, oh, that's it for the vocabulary and core concept check. All right, guys. So we are going to now officially, 45 minutes in about, get into the problem set. So we have a bunch to do, probably a bunch of graphs to be had. Let's go ahead and get started ASAP Rocky. All right. In exercises 5 through 10, determine whether the equation represents an exponential function. Explain. Well, exponential functions need to be in the form y equals ab to the x power, like this. Or they can be represented that way. If these aren't represented that way, then they're probably not exponential functions. I wanted to copy and paste these and get them ready, so I got this copied. So y equals 4 times 7 to the x power. This is very much in the form y equals ab to the x. Yes, in y equals ab to the x form. I guess it's faster for me to write that, unless I copy and paste that. I'm going to copy and paste that. That looks really weird, but I'm going to do that. Number 6, negative 6x. No, this is a linear function. Linear functions are not exponential. You can see x is not in the variable here. So y equals negative 6x. No. Linear function, and don't forget how those work, right? Don't take the new stuff you're going to learn now, which is a lot. Exponentials are nonlinear, and exponent is in the variable. This one, variable is in the exponent. This one does not have a variable in the exponent. Number 7, y equals 2x cubed. There is an exponent, but the variable is not an exponent. This is also a no. This is what's known as a cubic function, as it's cubed. There's a constant in the exponent, not a variable. I'll say not x. We need x in the exponent for those. Number 8, oh, this is perfect. This was my negative 3 to the x power thing that I mentioned. Yes, this is good. This is also y equals ab to the x form. I just mentioned it. If you missed it, I just mentioned this on the other thing here. Yes, this is in y equals ab to the x form, in that b is not negative 3. B is 3, actually. A is negative 1. It's a times b to the x power. What we have to know is our order of operations is that exponent comes before multiplication. It comes before subtraction, if you want to say it that way. And if you wanted to have something supersede exponents, use parentheses. Although that would not be an exponential function. Case in point, number 9. Number 9 is not an exponential function. B must be between 0 and 1 or greater than 1. So not exponential. You might say, Mr. Robinson, there's an exponent in the variable. I keep saying that. It's like when I say point your plots instead of plot your points. Mr. Robinson, there's a variable in the exponent. It's still a no because B is less than 0, which is not okay. It's not okay for B to be 0 either. B has to be between 0 and 1 or greater than 1. That's it. Positive numbers that are not 1. You can say it that way. Number 10, y equals 1/2 times 1 to the x power. Once again, B is 1. Just because it's an ab to the x form is no good here because b cannot equal 1. Were there more no's than yeses? B cannot equal 1. To be exponential, it needs to have exponential growth or decay, right? It needs to have that pattern. Multiplying something by 1 over and over doesn't change it. Doesn't change it. Okay. In exercises 11 through 14, determine whether the table represents an exponential function and explain. What we're going to look for is a constant ratio of y's as x increases by a constant amount. So let's take a look at this here. And x, by all intents and purposes, I believe x should increase by a constant amount. Otherwise, it'd be very tough for us to determine what it is we like to determine here. So on number 11, we can see that x is increasing by 1 each time, which is great. Fabulous. Question is, what's y doing? We're multiplying by 5, and then by 4, and then by 3. There may be a pattern that you see that doesn't make it exponential. Because this is not constant ratio, therefore not exponential. Exponential. So it's not a constant ratio, therefore not exponential. Okay. Number 12. X is, as you say, increasing by 1. Now y here, and again, it's about a ratio. Ratio means a fraction, right? It's like, whatever I would say, common difference. Maybe you remember that, maybe you don't. But when there's a difference between two terms, you're technically subtracting between the two terms to figure out what the difference is. But then you can apply that difference by adding, right? If I want to find the ratio between, because the difference between these is 1, because 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. But here, 12 divided by 6 is 2, therefore I multiply by 2 to get here. 24 divided by 12 is 2, therefore I multiply by 2, and 48 divided by 24 is 2. These have a constant common ratio. This is exponential. I'm just going to kind of point to the fact that all those are 2's. So it's exponential for that reason. I guess once I draw those out, it's good enough, right? Number 13, a sideways table. Hey, I've heard of those. So on this sideways table, x's are still increasing by a constant amount. We're adding 1 each time on x, so now we can compare y's as far as common ratio goes, and that's all that we care about, because they do not feature common difference in exponential functions. So as we're adding 1 each time here, the question is on y, what's happening? Now let's say you don't know what 0.25 times what number is 1. First of all, you could do division to figure it out, but second of all, lean towards some of the other numbers first if you want. 1 times what is 4? Oh, 4. Now we could ask ourselves, is 4 times 4 16? Yes. Is 16 times 4 64? Maybe take out your calculator, but yes. Is that what we do for 0.25 times 4 to get 1? Yeah, 4 quarters is $1, if that's a way for you to remember it. So this too is exponential. Constant common ratio. Number 14. 14 might be one of those tougher ones to talk about what we're multiplying by. I'm just going to spoil it right now. This one is not exponential. Now, if I wanted to ask, if I said, hey, 10 times what number is 1, 1 times what number is -8, things like that, we could figure out those numbers and they'd be a little, they're mostly fractions. I'll tell you right now, as x is increasing by a constant amount, it's not because these are +3s that this is an exponential. That's still a constant amount. That's okay. That's a lot. But what we're looking at here is 10 times 1/10 is 1. 1 times -8 is -8. -8 times 17/8 is -8 over 17. And -17 times 26/17 is that number there. So, whoa, Mr. Robinson, why did they come up with such weird numbers? Actually, what they're doing here is this is not exponential, but it does have a different kind of pattern. It's actually linear. We're subtracting 9 each time. Is subtracting 9 indicative of something that's exponential? No. Exponentials are non-linear. This is not exponential simply because it's linear. Now, we also showed that it didn't have a constant common ratio. We got to really weird numbers and fractions and changes in sign and things like that to show that it's not, but this is actually a linear function. That's all I wanted to state on that. All right, we're going to evaluate the function for the given value of x here. On these ones, we are dealing with some positives, some negatives. Doesn't appear we're going to do 0. Just as a reminder, 2 things. Number 1, PEMDAS, order of operations. You do exponent before multiplication on these problems. And number 2, negative exponents are a form of division, not turning numbers negative. Let's keep that in mind. All right, y equals 3 squared, substitute 2 for x. So y equals 9 is the value there. Very simple one. Number 16, f of x equals 3 times 2 to the x, where x is -1. 3 times 2 to the x, and x is -1. Let's evaluate f of -1. That means a substitution of -1 here. So 3 times 2 to the negative first power. Now, a negative exponent is the same as is flipping this fraction here. This is multiplying here 3 times. And then flipping the fraction, turning the exponent positive. That's 3 times 1/2, or 3/2. That's a good answer. 1.5 is another valid answer. 1.5, it might be nice to turn things into decimals sometimes because our point of evaluating here is we're going to be graphing, plotting points with graphs. So every so often you might have to tell yourself something as a mixed number or a decimal in the case of that, because how do you graph 3/2, right? You got to know it's like 1.5, that kind of thing. That being said, they're also gearing you up for graphing probably by use of a table when you substitute values in here. I mentioned this in the long lecture portion that I had, about the 45 or whatever minute lecture portion, that I do not intend on graphing using a table. I'm going to let you know that right now. I do have my tips and tricks of going about it. They are based off table usage and what you just saw above and before, but we're going to be utilizing these in a different manner. So negative 4 times 5 squared, once again, order of operations takes place. I got to do 5 squared first, which is 25. 5 times 5, not 10. And negative 4 times 25 is then negative 100. Okay, number 18. We have, once again, a negative exponent. Now, this is one where I want to try and do it without a calculator, if possible. So check this out. Here's what I'm going to do. F of x equals 0.5 to the x power, and x is negative 3. Here's what I'm going to do. First of all, we're going to substitute negative 3 for x, but I'm going to turn 0.5 into 1/2. You might know that 0.5 is 1/2, and this is just something that's more helpful for me personally. To the negative third power. Now, when you raise a number to a negative exponent, it's the same as putting it in its denominator, turning the exponent positive, but putting something in the denominator just means dividing it. So what happens when you divide a fraction? You multiply by its reciprocal. So if I want to turn this exponent positive, I got to flip this fraction, 2 over 1. Now I'm dividing by the 1 and multiplying by the 2, right? That's just how that thing works. 2 over 1 is 2, and 2 cubed is 8. So f of negative 3, the y value when x is negative 3, is 8. That's without a calculator. Now, I can do a lot of that kind of more so in my head, but I wanted to give you the properties and examples of that. So just as a reminder, we've seen this now in numbers 16 and 18. Negative exponents don't mean negative numbers, right? This was positive before, it's positive after. This was positive before, I guess, it's positive after. Negative exponents mean division, not negatives. We actually have established that something that was positive will stay positive, by and large, for exponential functions. They won't cross 0 or turn negative, even with negative exponents, because it's how many times you divide by your number. So it's good we're practicing these regardless. I wish there was one where we substituted 0. It doesn't look like we get to do that. F of x equals 1/3 times 6 to the x power, where x equals 3. Let's take f of 3. This is 1/3 times 6 cubed. We do have to do 6 cubed first. That is 216. So we will do 1/3 of 216, which is 72. F of 3 is 72. Remember, this is the y value when x is 3. That's what that means. Which just goes to show again how sharp these graphs go. We only plugged in 3 for x. What started at 1/3, it started at 1/3, and 3 away it got up to 72. That's how sharp these exponential functions can get over time. Absolutely. Let's see it on number 20. Y equals 1/4 times 4 to the x power. Again, we have to do the exponent first here. We can't just say, oh, 1/4 of 4 is 1, and 1 to the 5th is 1. No, that's not how it works. We got to do 1/4 of 4 to the 5th power. 4 to the 5th power, wait, I think we saw this in the example in a lecture portion. That is 1,024. Hold on. So a quarter of 1,024 is 256. You know, there are some numbers that you actually learn over time. Like I do over time with, I guess, from teaching and things like that. But powers of 4 are also powers of 2. So these are numbers that you see familiarly. Sometimes, like, I didn't do a true division here. I said, oh, it's in the 250. Oh, it's that 256 number. I'm aware of it. So it's also 16 squared. There are some numbers that kind of stick out that you get used to over time, and this is among them. It's kind of like, like multiplication. Okay, and exercises 21 to 24 match the function with its graph. So we're almost in the graphing stages, but they want to build up just a little bit more over time. We have f of x equals 2 times 0.5 to the x power. Now, I want to state as much as I will regarding how I'm going to do the graphs, but more so how we can determine which one's which. Because when we look at all these, I'm going to write them all out right now. Number 22, y equals. What we have in the first one is a positive, what's going to be our y-intercept, but a positive function. And the 0.5 is a number that's between 0 and 1. That represents a form of decay, exponential decay, which means as x increases, your y values, I'm not going to say decrease, but they get closer to 0. So when we see that instance, positive exponential decay, we're looking at a very specific appearance of graph. I could point to these straight up right now without doing any official calculations. Positive exponential decay is this one. This is C. And don't worry, I'll get back to these graphs in a bit. But this is C. Number 22, negative 2. This is negative exponential decay. That's B. This is just without looking at anything else because these are all unique. Number 23 is positive exponential growth. That's A. And then D must be the last one, but let's see. negative exponential decay on part D, on number 24, is graph D, right there. So let's go back to these graphs and talk about what's going on, because I'm going to do, looks like we're going to be graphing next on 25 through 30. So let's go back and take a look at them as a whole. On number 21, which is C, by the way, number 21, 2 represents your y-intercept. Notice that this is where we cross the y-axis at 2. Boom, right here. 0.5 is our decay factor. Every time x increases by 1, we multiply by another 0.5. Now, you just heard before, 0.5 is the same as 1/2. Multiplying by 1/2 is the same as taking half of something, dividing it by 2. So every time x increases by 1, every time I go right 1, I'm going to divide my y value by 2. 2 divided by 2 is 1. Then I go here, divide it by 2 again. 1 divided by 2 is 1/2. This is not a slope. It's not down this over this, down this over this. This is how close I get to my y-intercept, it's my x-axis, or my asymptote, if you will. And you take a half of a half, which is a quarter, things like that. If I'm taking half going to the right, then I'm doubling going to the left. So 2 times 2 is 4, etc. Anyway, this is very indicative of this equation. That's actually what matches it. Number 22 has a y-intercept of -2, but it's the same decay rate as this other one here. -2 is the y-intercept, so it's a negative exponential function, but its decay gets it closer to the asymptote from the negative side. -2 divided by 2 is -1, divided by 2 is -1/2, divided by 2 is -1/4, and you double this way, -4, and then -8, etc. So it's the exact opposite, flipped over the x-axis. It's the exact opposite of what 21 was in that way. These ones have exponential growth. 23 is positive exponential growth. You can see the y-intercept is 2, but also it has a doubling growth factor. Every time x increases by 1, you double this amount. 2 times 2 is 4. 4 times 2 would be 8. And if I double going this way, then I take half going this way. Divide by 2. 2 divided by 2 is 1. This is how I'm going to do my graphs, guys, without use of a table. I'm going to talk about the y-intercept, or my reference point I begin with, and then my growth factor, how far I distance myself from the asymptote. And then number 24 is -2 times 2 to the x power, etc. It's the same as 23, except in the negative realm. This is negative growth. Here's -2 as a y-intercept. It stays negative as we times 2 and get -4. Like I said, I call that negative growth. Not just me. That's the phrasing. We're growing largely negative. It's technically getting smaller, right, as actual values. But the negative numbers are getting bigger. And there's nothing inherently bad with that. Depends on the situation, right? So there's the thing. And then we divide by 2 going the other way. So I want to stress this importance now. We're going to go to numbers 25 through 30. They probably would have graphed using a table. I will not. So on numbers 25 through 30, if you're jumping into this part of the video for the first time without having heard the lecture on my graph stuff, which is a long lecture, I'm not sugarcoating it, guys. It is a long lecture. It's about 40 minutes worth. In the graphing portion, I'd probably speak at least 20 minutes on it. It's a long lecture. Or if you didn't even hear this little part on 21 to 24, I urge you go back to those things, because this may be a solution guide, but my goal is to teach the material. If my goal is to do the material, I'd be done with this video already. But my goal is to slow down and teach it. But I already did the slowing down and teaching, if that makes sense. So now I'm going to not fully whiz bang, but I'm going to talk about these a little more quickly. We do have more things to do, though. They do say, compare the graph to the graph of the parent function, describe the domain and range of f. Now, the problem that we have right here is f of x equals 3 times 0.5 to the x power. When they say compared to the parent function is some sort of, I'll call it g of x. It's 0.5 to the x power. So it's the same as this one with the b value. We can't change that into like a 1 or something like that. So we keep that the same. The question is, how does the 3 change it? But really, my ultimate goal, guys, I'm not going to be graphing the parent function as a whole. Now, here's the kind of graph paper I'm going to be giving y'all. These axes right here. Hold on. My copy paste doesn't always work here. These axes right. Come on. Copy. Can you please register the copy? There it is. Okay. These graph paper things right here. Okay. Now, I don't care about the negative values because this will be a positive decay function. Here's where I'm going to start each graph. I did not talk about this numbers 21 and 24, but the horizontal asymptote. This graph will never hit 0 for y. Ever. Never, ever, 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 ever. We're going to graph this. Let's see. Let me change. I can't make this blue because I'm going to graph this thing blue. So we're going to change. I don't know why I said the word change. We're going to start with the y-intercept here. When x is 0, y is 3. Plug in 0 for that, see what happens. We get a y value of 3. Your b value is your decay rate. Every time x increases by 1, you multiply your 3 value by another 0.5 from before. That also means multiplying by 1/2, which means dividing by 2. X increases by 1, I divide 3 by 2. 3 divided by 2 is 1.5. They start you straight off with some decimal work this way. 1.5 divided by 2 is 0.75. It's 3/4. 0.75 divided by 2, even if you know it was 0.375, you're taking half of 3/4, which is 3/8. Yeah, I just bit my tongue. A little less than a half. Point is, it keeps shrinking over and over. But it keeps shrinking to the extent that it never actually hits 0. Right? I only scale as well as I can in those situations, but it never actually hits 0. It gets close to it. Never hits it. Never turns negative. That's what the asymptote is featuring. If I'm dividing by 2 going this way, taking half of my values, then I'm multiplying by 2 going this way. 3 divided by 0.5, 3 divided by 1/2 is 3 times 2. That's 6. 6 times 2 is 12. 12 times 2 is 24. Now 24 doesn't fit on this thing, so I'm going to give you a couple heads ups on these graphs because you're probably printing them out for yourself or what have you. You'll notice there aren't numbers here, but there are little increments of 5 right here, and right here. So this is 5, 10, 15. That means the top of my graph is 17. This is something that I'm all too familiar with because I've used this graph paper a lot over the years, specifically on exponential functions. But just note that that's how I'm going to get things done pretty fast on these. I'm not counting so much as I'm comparing them to those increments or from the top of the graph right there. So I know that 24 can't fit on the graph because 17 is the top. So here's what I do. You connect with the curve. It is nonlinear. Connect with the curve. Please draw arrows at the end. You'll see me draw half arrows at the end of this one. Okay, we still have to do a couple things. Compare it to the graph of f. Well, compare g to f to the graph of g, I should say, because my graph of g is my parent function. So the graph of f is a vertical stretch by a factor of 3 from g. From g. Now, a vertical stretch does mean it changes the y-intercept. This one would have had a y-intercept of just 1. Boom. I'm not going to truly graph it, but 1 right here, and then you take half of 1 and you double this one and you get 2 and 4 and all that stuff, and I showed that in the lecture portion before, but that is 3 times smaller at every x value for the y's than it was before. Now the domain and range, domain is going to be all real numbers in all these. I can't see any time that it's not for non-contextual problems. Expect all real numbers. Range, compared to the asymptote here, our y values must stay positive. It hits every positive number eventually. The billions and the microfractions. But it never hits 0, it never hits negative. The range is y is greater than 0, or f of x is greater than 0, whichever way you want to state it. Number 26. F of x equals -4 to the x power. Now don't be fooled into thinking that this is not an exponential function. It very much is. It might help for us to identify what this is in terms of a, b to the x form. This is f of x equals -1 times 4 to the x power, where when you compare it to your parent function g of x, that's going to be 4 to the x power, or 1 times 4 to the x power, right? That's the difference. That's always a positive one. In this case, it's a -1. 4 is that value. So without use of a table, what will this graph basically look like? Well, it is negative this time, so I might need more room over here. Downward. I want you to see everything downward here. So, first of all, I still have a horizontal asymptote at y equals 0. You will always see a horizontal asymptote at y equals 0 as long as there is no plus k, plus 3, -7, whatever it is, it'll stay right there. So these graphs, that's where it'll be. You see number 31, it's going to change a little bit. -1 is the y-intercept, compared to what would have been +1 right here. Would have been up here. So what's the difference between these two graphs? It's a reflection over the x-axis. -1 versus +1. From there, multiply your numbers by 4 as x increases by 1. -1 times 4 is -4. Instead of 1 times 4 is 4. -4 times 4 is -16, which does fit on this graph. It wouldn't have fit on some of my other ones there. It goes sharp, very sharp. The next one would have been -64. Clearly can't fit that. This isn't a slope. It's a growth factor. Notice that it's not 4 away from the previous value. It's 4 away from the asymptote. 4 away from there, 16 away from there, like that. Not like 4 down from here, okay? That's multiplying by 4. Let's divide by 4 as we go this way, right? Multiply by 4 as we increase, divide by 4 as we decrease. That's a quarter, and then 1/16, etc. Getting super close to 0, never actually becoming it. Getting super duper close to 0 here. Now, my curves will not look great. My tablet and stylus, etc. doesn't really work toward perfection. And I actually employed a cardinal sin there. Try not make your graphs go vertical. Remember, the domain is all real numbers. That means it keeps going onward to the right. I'm trying to make it not go fully vertical. It's just super sharp. Remember, it's going to hit y equals 64 at x equals 3. So it's just one away that it's going to hit that. That's quite far out. So it does go very vertical-like, but not exactly vertical. So how does the graph of f compare to the graph of g? The graph of f is a reflection in the x-axis from g. Okay, that's the comparison between the two there. Keep in mind, this would have then had a y-intercept of 1, and it would have been positive exponential growth. This is negative exponential growth. The domain of this one, of course, all real numbers, but the range of this one is now underneath the x-axis. Only negative numbers exist here. Range y is less than 0. Okay, number 27. F of x equals negative 2 times 7 to the x power. Let's dive right into that there. Does look like it's going to be negative because we start with y-intercept is negative. Start with negative 2. Then we multiply by 7 as x increases by 1. That's negative 14. Here's negative 15. So negative 14 is right there. Divide negative 2 by 7. I don't know, negative 2/7. It's around negative 0.28 or something. Whatever. The point is it's less than negative 1, or it's closer to 0 than negative 1, things like that. It's quite sharply down. You take a seventh of what there was before. I have a fly that's flying right in here. That's not going to be fun. Anyway, so that's really as much as I can actually plot to make it nice here. I might have to pause this thing in a second and swat a fly in a second. Anyway, so there's the asymptote that we approach. We never actually hit it, right? This looks like, oh, it's going to crash right through there. Nah, it's still not. This thing, you divide that by 7, it just gets really close to 0 here. Just works its way through. So let's see if I can get this done. I'm absolutely, I have to pause this video, guys. Give me 1 second here. All right, I very quickly realized I don't have a fly swatter, so I don't know where it came from. It hasn't flown in my way since I paused the video about 15 seconds ago, so I'm just going to keep moving forward. If it comes in my way, it comes in my way. I'll mention it, or I'll ignore it, or whatever. Not a very well drawn curve. Hopefully they give us like less sharp curves so we can accentuate these a little less than that. But that's how sharp this thing goes. Now, how does this compare to a function that would have been non-transformed from that base of 7 to the x power, right? First of all, that y-intercept would have been 1, a positive 1. Not a 2, which means it's vertically stretched, and not a negative, which means it's reflected over. So those are two things that are changing. The graph of f is a reflection in the x-axis from g, followed by a vertical translation, stretch by a factor of 2. I hope I didn't call something else a vertical translation before. I should have said stretch. Let's see. Should have said stretch. Yeah, I said stretch. Okay. So it's both of those there instead of going up in that way. They still do times 7 in that direction, but with a different y-intercept, right? Number 28. Oh, sorry. Before I do 28, let's do domain and range. Domain, all real numbers. Range, y is less than 0. So these will seem a little repetitive, but we got to understand a couple things. We still have to affirm how domain and range work and how exponential functions work. The idea of this limited range, this asymptote feature, things like that. Number 28, f of x equals, it says compared to the graph of the parent function. Maybe I am supposed to graph them. I have enough on my plate already. Number 28, f of x equals 6 times 1/3 to the x power. So this one has, well, it's positive this time, right? This one has Same horizontal asymptote as it ever was. 6 is the y-intercept. When x is 0, y is 6. When x is 1, y is 6 times 1/3. You multiply by 1/3. A third of 6 is 6 divided by 3, which is 2. Take a third of 2. You get 2/3. Or 0.6 repeating, right? That's kind of weird, though. 2/9 is next when you multiply 2/3 by 1/3, which it just gets really small, right? Gets closer and closer to 0. Never quite touches. There's that direction. 6 divided by 1/3 is 18. Because it's 6 times 3. Now this is 17. So 18 would be 1 up from there. I'll gladly plot it. The idea of it as, oh, I see the fly. I see the fly. Here it comes. Oh, I didn't really quite get it. It has come back. It's going to mess up my graph. Exponential functions, y'all, super tall. Okay. So there's that one. You know what? I'm happy to say that I've already completed my exponential graphs for IM2 and IM3. Maybe after the section and reviews and things like that, I don't have to go and do them anymore. I'll feel pretty good about that. There's no problem with the graphs themselves. It's just these curves are really hard for me to do on my tablet. That's all. My g of x original equation would have been 1/3 to the x power. Now you do have to have this thing in parentheses whenever it's negative. Well, I guess it won't be negative, but whenever it's a fraction. Because both portions of the fraction need to be raised to the x power. Just a little syntactical thing. Okay, so how does the graph of g compare to here? Well, this would have been a y-intercept of 1, of course. So this is going to be 6 times taller. So the graph of g, or the graph of f, is a vertical stretch by a factor of 6 from g. Domain, all real numbers. Range, y is greater than 0. Number 29. You have f of x equals 1/2 times 8 to the x power. It's going to get super tall, super fast, but it starts super short. It starts super low. It starts at 1/2. We generally don't talk about y-intercepts being fractions, but here we are. So this is 1/2, and the good news is when we multiply it by 8, it becomes an integer immediately. Bad news is it gets pretty tall over time. 1/2 times 8, as x increases by 1, half of 8 is 4. That's not tall, but 4 times 8 is tall. 4 times 8 is 32. I already can't fit that on this. 32 is almost double the height of what this one is. So that's so tall that this will look very vertical in our eyes. Heck, I have to divide 1/2 by 8 going this direction. I get 1/16, right? That's 1/2 times 1/8. So there's so few points I can plot here with respect to, well, with respect to my scale, my chosen scale. And I don't think most people are going to change the scale, so it goes up to 34, or 32, I should say. But that's actually not too bad of a curve there. I've done significantly worse. You've already seen some significantly worse. Anyway, you always still see me do those half arrows here, and there's the appearance of it. Now this compares to g of x equals 8 to the x power. Again, 1 times 8 to the x power. So this is a vertical change, only it's no longer a stretch. This time it's a compression. The graph of g, you thought this one was tall at x equals 2. The other one would be at 64. The graph of f is a vertical compression, or shrink, by a factor of 1/2 from g. Y-intercept of 1/2 instead of 1. This would have been at 1, then 8, then 64. Then again, this would have been 1/8 instead of 1/16, but that's still short anyway. Last one in this part, number 30. F of x equals 3/2 times 0.25 to the x power. Now, besides the fact that neither are integers, the other thing I'm quite not a fan of personally is that one's a fraction and one's a decimal. If push came to shove and I had to do something, especially without use of a calculator, I would use fractions. You're like, what? This is maybe one, guys, where we might want to use a table, not because... I might want to use a table just so we can see the values for what they are and when we compute them. I am going to turn this into 3/2 times 1/4 to the x power, and we can talk about those things a little bit more in full. I will still be plotting points, but I will actually emphasize by use of a table here. I personally wouldn't be using a table, but but I want you to see how this computation works with fraction on fraction. It's fraction on fraction crime, guys. That's exactly what this is. So x, y, y's, we're going to get some values out, probably -3 to 3. Let's see how far we can go with this. But I'm not going to change the idea of what I do. By table, I don't mean substitute values for x. I mean write my values for y. That's literally all I mean. So I'm going to start from 0. When x is 0, y is 3/2. That's still the y-intercept. There's no change on that. And 3/2, by the way, is 1.5. So that's the other portion of this. We got to know how to write out our mixed numbers from what this is. Now, 1/4 does mean decay, means your numbers will shrink. I got to do 3/2 times 1/4, that number times 1/4, and that number times 1/4. You can bet that these numbers are going to get pretty small over time. 3/2 times 1/4 is 3/8. 3/8. So how do I plot that? Well, it's a little less than 1/2. Maybe right there. 3/8 times 1/4, this is already too small to really make mention of, but 3/32, pretty much 1/10, a little less than 1/10, very small. Not quite as small as 1/16, but it's hard to distinguish between the two anyway. And that times 4 is, well, 3/128. It can't reduce, but that's so small, it might as well be 0, but that's the point. It never actually is 0, and that's why I bring that up. Now here we get to multiply by 4. Now here's the cool part. Right? Divided by 1/4 is times 4. Times 4 is 4 divided, I like to do the fraction first. 4 divided by 2 is 2. 3 times 2 is 6. So we actually get 6 right here. The problem is it's already going to go out of range. Times 4 times 4, so it's probably, I probably went a little too big on these, but 24 and then 96. 24 alone I can't fit on there. This is 17. But those are the indicators of how we're doing what we're doing. Now, I didn't get to play with mixed numbers, really. 3/2 is the only time I would have. These turned into integers right after that. I didn't think about the fact that would happen. But this is positive exponential decay. It would have hit 24 up there. Would have gotten pretty close, but I don't quite get there when x is -2, so I don't reach it. And that's the point I want to make, right? You plot as many points as you can fit, but for points that you can't fit, don't cross the threshold where they would have fit. I shouldn't hit x equals -2 right here, -3, unless I had points to calculate. And if I do, I should be plotting them. So there's the graph. Now this compares to, keep in mind, this would have been compared to g of x equals 0.25 to the x power. I don't need parentheses around it, but 0.25 or 1/4 to the x power. This is slightly bigger, barely. It's 1.5 versus 1. 1.5 times bigger. The graph of f is a vertical stretch by a factor of 1.5 from g. That's it and that's all. Now domain is all real numbers. Range is y is greater than 0. We're above. Even though it's decay. Okay. Those are 6 graphs right there. I did it faster than use of a table, arguably. And that helps us moving forward. We have 6 graphs to do, probably with translations. So let's get ready for those. Keep in mind, I do it slightly different from the book with the same outcome. Probably a better overall outcome when it comes to how I do later graphs with my videos. If you plan to follow me into IM2, IM3, you're going to want to learn the tableless graphing formats that I have. It says, graph the function, describe the domain and range. This time we don't have to compare it to another graph, which is better for myself personally. That being said, they would probably graph a parent function, 3 to the x power, and then shift it 1 down, which is what's happening. But here's what I'm going to do. I'm going to, remember that asymptote? Dead asymptote? We are going to take what would have been 0. Everything is 1 less than it was before. That's what the -1's all about. It's a vertical translation 1 unit downward. This also translates 1 unit downward. And I want to start with the asymptote. I want to start 1 unit lower than I was previously. That's a big thing for me, personally. This x-axis to me is now non-existent. I couldn't care less about it. This is what I care about now. This is like my y equals 0 in a way. Everything I do will now be in relation to this because everything will be subtracted by 1. I'm just going to do it from here so I don't have to subtract 1 myself. I say all that wanting to go a lot faster right after this. Now remember, this is 1 times 3 to the x power minus 1. This 1 is my a value. My a value would have been my y-intercept, but now it's just how far I am from the asymptote. I'm 1 away from the asymptote right here. You can try and plug in the number. Let's try this just for this problem. f of 0 is 1 times 3 to the 0 minus 1. 3 to the 0 is 1. 1 times 1 is 1. 1 minus 1 is 0. The y value is 0, which is 1 up from the asymptote. So that's how my a applies. B applies the same way as before, but it's distance from asymptote, not from the y values. I don't say 0 times 3 is 0, so I keep 0 here and times 0. It's times the distance from asymptote. So 1 times 3 is 3. 3 times 3 is 9. The only problem now is we got to go 9 up from the asymptote, and which is 1 lower than, you know what I mean? I might have to do a little bit of counting sometimes this time. 9 times 3 is 27. I can't fit that or 26 up, whatever, from 17. So that's good there. 1 divided by 3 is 1/3, and 1/3 divided by 3 is 1/9, and we continue in that process. So this is the graph. If you graphed y equals 3 to the x and translated everything 1 unit down, that's fair and that's fine. It takes a lot more artistry. You have to take your pencil and do it. Here's the thing. I could take my graph, listen, I'm on a computer. I could take this graph, and I could have graphed it right from here. This is y equals 3 to the x. And then I can translate it 1 unit down. I have the ability of making that happen. Boom. There's the 1 unit translated down. But every point goes 1 unit down. That's why I do things in relation to the asymptote. Now, the domain's still not going to change, guys. This is all real numbers. But the range will change because now y values don't approach it. In fact, we can hit some negative numbers. We can hit everything down to -1 without actually hitting -1. And that's the point. Y has to be greater than -1. The k value determines our range. Number 32. F of x equals 4 to the x plus 3 power. All right, this depends on what you remember about horizontal translations. I'll make one analogy with this at this time, and I'll see if I want to stick with it later. But or not analogy, but one table tie-in, meaning substitution of a value. First of all, there's no plus k here. That means the horizontal asymptote is at y equals 0 once again. The a value is that 1, right? At some point, I'm just going to state that it's implied, but that's our how far we'll go up from the asymptote. But the thing is, this now has a horizontal translation. When it says a plus 3, remember it's opposite. It means we go 3 to the left. 3 to the left. So 3 to the left is when I have a point 1 up from here. So let's check this out table-wise and why this works. Let's do f of -3. Why does this happen this way? That's 4 to the -3 plus 3 power. -3 plus 3 is 0, and 4 to the 0 is 1. If you put the 1 out here, 1 times 1 is 1. We're plugging in the x value that gives us a 0 exponent. A 0 exponent wipes out your b and leaves you with a. That's why we shift this many units to make this reference point that far up from the asymptote at that translation, which is opposite of what's there. We need the opposite of that to make that thing 0, and that's how that's going to happen. There's my translation. From here, it's all about the 4. It's all about the 4. Every time x increases by 1, we do times 4. Increases by 1, we go times 4. We go 1 less, it's divided by 4. And we get to 1/16, etc. So it goes that direction like that. There's a translation. If you did it from the original graph, you would just graph y equals 4 to the x power, which is a y-intercept of 1 as it stands. And then you would translate it 3 units to the left, and this is what you get, right? Again, when I'm on a computer, I can show you, I can demonstrate exactly that. I can say, hey, this is where we would have started, right here. But now we move it right there. 3 units left. Domain is all real numbers. Range is y is greater than 0. We haven't changed anything there. Just because we shifted something left doesn't change our domain of being all real numbers. And the range is still based off the asymptote that we have. Number 33. Couple transformations on translations. We have y equals 5 to the x minus 2 power plus 7. This has both vertical and horizontal translations. I begin with vertical. I'm going to start with this plus 7, just like this. Boom. We're going to start 7 units higher than before. Everything's going to be in relation to the asymptote. Now, I'm not going to be able to plot very many points here. I'm just going to let you know right now. The minus 2, x minus 2, is shifting 2 to the right. My first point, which is 1 unit up, by the way, 1 unit up, I'm going to be shifted 2 to the right for it. I already indicated as to why that is, and same with the 7, so I'm just going to leave it like that. Now it gets multiplied by 5. 5 units from here, right? Or 5 times from here. 1 times 5 is 5. 1, 2, 3, 4, 5 is right here. 5 times 5 is 25. I, of course, can't fit that one. I would have been able to, if this had minus 7 and we're shifted down there, then yeah, I could probably go 25 up from there. Unfortunately, this is the graph. 1 divided by 5 is 1/5. When I say unfortunately, I'm kind of blessed because I don't have as much to draw. Therefore, neither do you. But I like to indicate where those points go and show that exponential form as I can. Domain's all real numbers. Range is now changed. Y is positive numbers greater than 7. They have to be above the asymptote there. Note this, and I don't know, because we don't do graphs after this. So this book, and I don't know when they start doing it, but this section does not mention the word asymptote, despite the fact they clearly show the idea of asymptotes here. So I'm showing a word to you that they're not. I don't know how good I feel about that, but I feel like I don't know why they're not showing it either. All right, this one's stressing the fact that there is a negative in front of the b value. Therefore, this is a -1. I have to keep highlighting that. We have a lot of things going on here. There is reflection making it negative, but we'll hit that when we just talk about our reference point. We'll just say it's below the asymptote instead of above, and we'll be good. Now, that being said, we have some other things to take care of. -3 is here. Let me do this. I'm going to move this up here because this will be a negative graph and it's shifted down. So -3 is my asymptote there. We are going to shift 1 to the left. Keep in mind it's opposite. And we're going to go down 1 for that. So what was before a y-intercept is no longer the case because we're now shifting 1 left and 3 down, if you will. But from here, we'd go 1 down as we go 1 left as well. The 1 down is from this. The 1 left is opposite of that. That's a reference point. Now we take our 1/2, we multiply that distance from -3 every time x increases by 1. -1 times 1/2 is -1/2. -1 times 1/2 is -1/4, and then -1/8, etc. Now we divide by 2 going this way. This is a nicer, slower progressive trend. So divided by 1/2 is times 2. -1 times 2 is -2. 2 times 2 is 4. Just 4 down, right? 4 times 2 is 8. And 8 times 2 is 16. Now, 16 down from -3 is -19. This goes down to -17, so I'm just going to go -18, -19, pretend like it's there. So I can just get this nice smooth curve in this exponential function, remind you of what we did here. As much as you are like, why don't you use a table, Mr. Robinson? Well, I don't know how quick you think it would have been to make a table, but what I did was significantly faster than that. Just giving use of that stuff. Efficiency. See, using a table might help you work your calculations out a little bit more on these things, in which case, confirm them for sure. But I'm still dealing with exponential functions the way they're supposed to be. Every time I decrease x by 1, I'm doing another division. Division of a fraction, but division here. So I'm keeping in mind how they still work. Okay, number 35. Oh boy. -8 times 0.75 is the x plus 2 power minus 2. I'm probably going to turn the 0.75 into 3/4, as 3/4 is 75 cents. 3/4 to the x plus, whoops. That plus was neither exponent nor not exponent. Okay, so -8 means we'll be below wherever we go here. The -2 is our vertical shift. That includes horizontal asymptote. -8 is our y-intercept. Or, well, sorry, our reference point. We're going to go 8 down from the asymptote if we shift 2 to the left. So 8 down, 2 to the left. That's a point on there. If you don't believe me, plug in -2 into here, see what you get. You should get -10 for y. 3/4. I got to take 3/4 of these numbers as I increase x by 1. So this is the part where, again, a table will help on these things. And when I say table, what I mean more so is not even, I don't care what the x's are, honestly. I just care about y values. I just want to know what -8 times 3/4 is. That's all I care about right now. Couldn't care less that the x value is -2, -1, things like that. But because everything's just moving 1 over. So times 3/4. -8 times 3/4, -8 divided by 4 is -2 times 3 is -6. So I'm going to be 6 away from the asymptote here like that. That's 3/4 of 8. 6 times 3/4. 6 over 4 reduces to 3/2. 3 times 3 is 9. We get 9/2, which is 4.5. -4.5. So that's right here. 1, 2, 3, 4.5. negative, see, I want to keep them as fractions, really. Negative 9 halves times 3/4. I'm going to do at least, well, a couple more. I think it's worth doing it on this side as long as I can fit them. Negative 9 halves times 3/4 is negative 27 over 8. I'm just going to write them as fractions. Then I'll give you the, see, I don't care about the table. I just want to calculate things. Negative 27/8 is negative 3 3/8. So negative 1, 2, 3 3/8. The question always becomes, how many of these should you plot? That's a good question, to which the answer is not quite clean. I'm clearly not using the table. I'm just multiplying numbers here. So what's negative 27/8 times 3/4? And by the way, unfortunately, none of these are going to reduce the rest of the way. Negative 27/8 times 3. And by the way, you can totally probably use a calculator. This is negative 81 over 32, which is negative 2 and 17 over 32. So about negative 2.5. And then that times 3/4. There are only so many times I can do this before I say, and it's about right there, and it's about right there. So it's negative 243 over 128, which is less than negative 1.5, because that would be negative 256 over 128. Less than negative 1.5? How could that be more? How could that be? Is that right? 243 over 128. That looks like a different kind of jump there than that one is. I must have messed up on my jumps here. Let me think about that one, because I'm known to mess up some of my fractions here. 128. I'm sorry, that's not less than negative 1.5. That's less than negative 2. It's getting close to negative 2. That's why that looks so weird. That's negative 1 and 115 over 128. So actually, that's really close to negative 2. I totally messed up how I was saying that. I'll do one more. Times 3/4 is negative 729 over 512. That's less than negative 1.5. So probably about there-ish. And then, it keeps going, right? It's a very slow decrease. Now, if I go the other direction, I'm dividing by 3/4, which is multiplying by 4/3. So negative 8 times 4/3 is negative 32 over 3, which is negative 10 2/3. Now, negative 10 is 10 down from negative 2. So negative 10 2/3 is about right there. From the negative 2. Actually, yes, from there. Let's see if I can fit one more here. Times 4/3 is negative 128 over 9. 9 is 90, 99, 108, 117. About negative 14. About negative 14 and change. So, yeah, it's going to be about, here, whatever. Really close to something like that. So, that's my point, guys. This is one of those ones. That's why I said uh-oh when I ran into this one. But this thing has a very slow decay. It's negative decay. It's a very slow decay. And it would continue going toward the asymptote. I'm just going to give it still a progressive 3/4 of this, 3/4 of that, 3/4 of that, whatever. And it keeps working its way down. I appreciate those ones as far as seeing the curve for what it is. And as it gets closer and closer to there, less intensely. But you get a lot of fractions along the way. Clearly, you can probably use some form of a table. I'm just giving you the inkling of what you could do either mentally, what you could do with fractions, that kind of thing. Domain's still all real numbers. Range is still y is less than negative 2. We're still not going to hit anything at negative 2 or above on that one. This one should be a lot gentler because less use of fractions overall, but it looks like it'll be sharper as well. So number 36. Number 36, we got f of x equals 3 times 6 to the x minus 1 power minus 5. Now, by the way, that last question, whether you're like, oh, I would have been faster with a table. It depends on whether you would have done it with a calculator or not. Without a calculator, I still did that significantly faster. I want to stress that importance. Anyway. Here we can see our A, B, H, and K in full form. All of A, B, H, and K. I'm going to start with K. I'm going to start with K, and our negative 5 asymptote is here. And then from there, I'm going to plot the A value when I'm horizontally translated. I'm going to go 3 up when I'm 1 to the right. Everything after here will be about B. 3 times 6 is 18. 18 up from negative 5 is 13. 10, 13, right there. That's 18 up from there. That's as fast as I'm getting that one done. That times 6 is way too big, clearly. 3 divided by 6 is, well, it's 1/2. Half of, excuse me. Wait, I'm sorry. It is 1/2. It's not halfway up. So it's 1/2, literally. Halfway up from the asymptote. 1/2 divided by 6 is 1/12. So very, very sharp in comparison. Very fast compared to the last problem, but also very sharp. I haven't seen that fly in a while. Quite glad. Ooh, nice curve. It's because the fly was in the way before, I tell you. Hope it died. All right, domain. All real numbers. Go figure. Range y is greater than -5. You'll never get a value at or less than -5. Okay, guys, in exercise 37-40, compare the graphs, find the value of h, k, or a. It sounds like they're only doing one of these at a time. It's best that I probably copy and paste these graphs as we go along. Oh, they actually even give you a heads up on which one it's going to be. I didn't notice that. So they give you the parent function in black, the transform function in blue, and we're asked to determine what the thing is based off that. So comparing the graphs here, if we, well, I'm not going to say it's best to compare by y-intercepts always, but in this case, that might be exactly what I should do. The y-intercept here clearly is 1. We should be aware of that based off what that is, and we got to find that a. So this y-intercept appears to be half of what it is, and you can tell here that 1 is half of 2, and 2 is half of 4, and this kind of keeps working that way. So the graph of G is a vertical compression, vertical shrink, whatever, by a factor of 1/2 from f. That being said, we have an a value of 1/2. That's what the a value is not only, the a value, let's see, what is this? Find the a. The a value is not only the transformation aspect, though, it is also the y-intercept of a non-translated graph. Now, number 38 is a translated graph, and that's all it is. So we got to talk about the translation. And for me, it's all about the asymptote. I mean, they don't draw the asymptote, but you can clearly tell where the asymptote is, and hopefully that's a good representation of change here. Now, the original parent function is 0.25, which is 1/4. That's why it's decaying. It's dividing by 4, dividing by 4. But here you can clearly see you go from a horizontal asymptote at the x-axis to a horizontal asymptote at y equals 3. That is a shift of 3 up, and if there's no other way to tell that, it's by the y-intercepts. The y-intercept being 1 up from here. This is still 1 up from here, no change, but you can see everything shifted 3 up from before. So the graph of G is a vertical translation 3 units up from F. Jeez. That means the K value is 3. K equals 3. Okay. Number 39. Now we change h. This is a horizontal translation. You can see it's inside the exponent. It's inside the function itself, if that makes sense. The function is the exponent portion of it. So we are going to talk about the horizontal translation of that thing, because that's exactly what it is. Horizontal asymptote is still the x-axis, right? No change there. Our special y-intercept has now gone 1, 2, 3, 4 units over, and if that's the only change, that's the only one we have to note. This went 4 units right. This went 1, 2, 3, 4 units right. Clearly, it's a 4 units right thing. So the graph of G is a translation 4 units to the right from F. Therefore, H is 4. H is 4, and it is just 4. We don't say H is -4. The equation will say a x minus, whoops. The equation will say an x minus 4 inside of there. Cool. Whatever, it'll say x minus 4, but we don't say h is -4. It indicates that in the equation itself. Keep that in mind. Okay, and then we have number 40, where we once again change h. Another horizontal translation. Let's see if we can do this one a little bit more quickly. We still have to type out that part. But on number 40, knowing what we now know about these translations, this one's going left instead of right. Where this thing says a minus, remember, well, it might not end up saying minus ultimately if we wrote the actual equation. But compare a point. Let's pick a known point like this one and figure out where it's going like that. Yes, this might have been a y-intercept of 1/3, and this is the 1/3 there. That's just harder to detect. This goes 2 left. -2, right? 2 left, and that'll be our h value. So the graph of G is a translation 2 units left from F. Therefore, h is -2. Now, when it comes to writing the equation, not that we're actually writing, but I want to kind of give the idea. Now it's -2. Subtracting -2, this will turn into a +2 in the equation. The h value, though, is negative 2, right? That's how it works. 2 units left, that's h. Okay. What? Wait, was that? Oh, I must have skipped it. Oh, there were more problems down here. Okay, sorry. All right, number 41 and 42, error analysis. Let me fix my neck here. Oh, boy, guys. Here we go. All right, describe and correct the error in evaluating the function. Okay. It looks like an order of operations issue here. We substitute negative 2, all good and fun there, but they did 6 times 0.5 first. Now, 3 to the negative second power is actually 1/9. It's 1 over 3 squared, so that's actually fine. The problem is their order of operations, something I warned against. So they used an incorrect order of operations. Exponents calculate, I should say occur or calculate, before multiplication. Okay, so let's fix it. We will say, we'll start from that step there. G of negative 2 equals 6 times 0.5 to the negative second power. Now, I've been kind of big on showing this decimal as a fraction, especially if I'm not going to use a calculator. So this is 6 times 1/2 to the negative second power. And flipping the 1/2 into a 2 over 1 is what turns this positive. And we still, by the way, we still have to do 2 squared first. So 6 times 4, which is 24. So that's the fix of that one there, raising to the power and such. It's a way different answer from 1/9, although they're both positive, right? Negative exponents don't mean negative numbers. So that's 41. Number 42, describe and correct the error in finding the domain and range of the function. Assuming the graph is good, which so far everything that I'm looking at makes it look pretty good. It says domain's all real numbers, good. Range is y is less than 0, not good. The -1 here is indicating a vertical translation 1 unit down, which means asymptotically we actually have it right there, which means we'll never actually hit anything between -1 and 0. We won't even hit -1 either, right? So on number 42, the range is wrong. The range is wrong. The range is wrong. There is a vertical translation 1 unit down, which means they're not saying this phrase, but I want to say it again. The horizontal asymptote is also shifted 1 unit down. The range is y is less than -1. Yep, you're going to get numbers really close to 0, and then you subtract 1 from it, then you'll get numbers really close to -1. It's still underneath them. Okay. Now, exercises 43 to 44, graph the function with the given description. Compare the function to f of x equals 0.5 times 4 to the x power over the interval x equals 0 to x equals 2. I feel like we have to graph both of these this time. I feel like I'm not allowed to kind of change it unless I provided a table, but I'm probably going to avoid doing that too. All right, we have this f of x equals here. Let's read the description of this. We'll call it g of x, okay? Okay, an exponential function g models a relationship in which the dependent variable is multiplied by 0.25 for every 1 unit. The independent variable x increases. The value of the function at 0 is 8. Listen, I'm going to go straight to my equations. I know they didn't do that for these examples here, but we've been graphing without use of a table, and I'm going to continue that here as well. So I'm going to go into this. When they say at 0 is 8, the value of the function here, then we can refer to this as the y-intercept, therefore the a value. So 8 is the y-intercept, and then 2.5 here is the growth factor of this one. It's multiplying by 2.5 every time x increases by 1, and that's what this is. Now, these are way different graphs, guys. There's very little that's similar, except they're both positive exponential growth. No, I wasn't copying that. I was trying to copy the graph axes. There we go. All right, so for these ones, let's start with f. 0.5 is the y-intercept. First of all, these have the same horizontal asymptote right here, no shift. But we have 0.5 is the y-intercept, and they multiply by 4 each time. 0.5 times 4 is 2. 2 times 4 is 8. 8 times 4 is 32, unfittable. 0.5 divided by 4 is 0.125. 1 quarter of 1/2 is 1/8. So this is our f of x graph to begin with. Now, this other graph is kind of way different, all told. I don't even know what they want us to significantly compare. But let's take a look. This is going to start off not very well for my thing as an overall. 8 is my initial setup, right? Now from here, let me make sure. The value of the function at 0 is 8, and it multiplies by 0.25. Yeah, this is just at here. 8 times 2.5 is my next go. 8 times 2.5, 8 times 5 halves. 8 divided by 2 is 4. 4 times 5 is 20. Is 20. Okay, I'll force fit it. Here's 17, 18, 19, 20. But that's a little bit taller there already, right? It goes significantly taller there as it goes. 8 divided by 2.5. 8 times 2/5 is 16/5, which is 3 1/5. 3 and 1/5, like that. I'll do at least one more here. 16/5 times 2/5 is 32 25ths, so it's a little more than 1. 1 and 7 25ths, like that. So you can see the shrinkage there, but not quite as sharp. It starts taller. It doesn't shrink quite as fast as this other guy. It would kind of keep, working itself this way, like that, until it goes over. But those are the two graphs. I didn't change the scaling. It says compare them. I mean, it starts taller and stays taller. It says compare the function to this one over the interval. The value f of x, let's see, the graph of f is taller than g over the entire interval. I don't really know what they want me to say on that, because this, see, the lecture version had two that shared the same y-intercept. So there was actually something to compare. This one here, nothing really crosses over at any time, so I don't really know what they want me to say. But over the entire interval, it's different. I'm sorry. This is G. This is G in blue. This is F in black. Okay. Number 44. An exponential function h. Oh, what was the original? 0.5 times 4 to the x. Let's actually do this. Let's do this. I get to use the same graph. So I'm going to... Give me one sec. I have to find a way to copy and paste this. Okay, I've successfully brought it over. So let's go on number 44. Again, the original f of x was 0.5 times 4 to the x power. And we have a brand new g of x. Oh, h of x, excuse me. The exponential function h models a relationship in which the dependent variable is multiplied by 1/2 for every 1 unit the independent variable x increases. The value of the function at 0 is 32. Well, now I might have to change my scale. So this is 32 times 1/2 to the x power. Okay. Okay, I might have to change my scale. Well, if you're okay with us imagining, I do have a y-intercept of 32, which is pretty high up. That's when x equals 0. We know where it is, okay? When x equals 1, we multiply by 1/2. We get half of 32, which is 16. So we get this value right here. There's a 32 way up there. We're just not going to see it. That's okay. That's just a part of graphs. There are some points we don't see. Like I don't see the one at x equals 3 over here. When x equals 2, 16 divided by 2 is 8. Hey, they're the same there. And then 8 divided by 2 is 4. 4 divided by 2. See, otherwise we don't get all these other fun points. 4 divided by 2 is 2. 2 divided by 2 is 1. And then 1/2 and 1/4 and 1/8. So we get a lot of graph here, right? We get quite a bit of graph, and it would go up to 32 way up there. We'll keep that in mind because I think we have to compare from x equals 0 to x equals 2. Okay, so h has greater y values than f for everything up until x equals 2 when they then have the same amount. So both functions have the same value when x equals 2, but the value of h is greater. is greater than the value of f over the rest of that interval. Now, the interval goes from 0 to 2. I don't know why they're specific on those ones, but that's what we can say. It's greater than it, and that's still the graph. It still works. Okay, number 45. This is, I guess, a real-life problem set, modeling with mathematics. You graph an exponential function on a calculator. I guess it's not real-life application. You graph an exponential function on a calculator. You zoom in repeatedly to 25% of the screen size. I was going to write 25, and you write 45. The function y equals 0.25x represents the percent in decimal form of the original screen display that you see, where x is the number of times you zoom in. So if I zoom in once, I become 25% of what I was screen size wise. If I zoom in twice, it's 25% of that number, of that previous one. 25%, 25%. That's how that's working out. It says graph the function, describe the domain and range. So we have y equals 0.25 to the x power. That's also 1/4 to the x power, and I'm going to state that one out loud as opposed to actually rewriting it. Let's see if we can kind of keep that in mind when we're doing this. So for this one here, again, horizontal asymptote, boom, and a y-intercept of 1. I think at this point we have to understand that there's a 1 in front. Now 1/4 of, well, you know what I should do? Should I change my scale on these ones just because we're going to zoom in so much? We care about zooming in versus zooming out. I'm going to call this 1 and 2, 3, and 4. Changing my scale on y. My x is still as it was, 5 and 10, etc. When x is 0, y is 1. That's my y-intercept. We take a quarter. It's already going to shrink a bunch. We take a quarter of 1, and we get 1/4 like that. A quarter of that is 1/16, which is actually right there, right? So that's actually how those things work. Now we divide by 1/4, it's multiplying by 4. So I'm giving it a sharper look by stretching out the y's. It doesn't change the fact we still do multiplications by 4. So it's technically the same graph. It's just zoomed in and of itself, right? Kind of neat. So it says graph the function, describe domain and range. Well, the domain's still all real numbers. Well, it depends if we're doing zoom. Actually, I take it back. We're not starting. This is contextual. It might be talking about a calculator, but this domain, I don't know if we should graph anything to the left. To me, the domain actually just might represent, I'll do a dotted line version to say, I don't really know. The domain here to me starts at 1. Excuse me, starts at 0. I didn't do any zoom-ins yet. We start at 0 and we start zooming in more and more. We didn't zoom out. We start by zooming in. So that's where I feel the domain's going to be here. I feel like they're asking us a different kind of question this time. The range, if the domain starts here and we don't do zoom outs, just zoom ins when it comes to percentage, then 100% is the most that we get. So the range is now limited between, it's got to be above 0 here still, but it's got to stay under 1. That's how I'm interpreting this question. It says you zoom in repeatedly to 25%. You never zoom out. So that's how I'm seeing this graph. So this part I'm kind of taking out of here architecturally. So I could have changed the zoom on these quite a few times there, but that's what I'm going to say for domain and range. Part B says find and interpret the y-intercept. The y-intercept says that my original, calculator zoom is at 100% or whatever, right? It just says that I'm basically not zooming at all. The original calculator, let's see, the function represents the percent of the original screen. The original screen display is at 100% without any zoom-ins. The 100% is the y value of 1. It's kind of decimal equivalent of a percentage, right? And the 0 is without any zoom-ins. I zoom in 0 times there. And I don't know, honestly, I don't know if this should be a continuous function or not, but I'm just going to leave it like that. It says you zoom in twice. What percent of the original screen do you use? So zooming in twice is this value right here. So part C is when x equals 2. When x equals 2, y equals 1/16. I know that because I'm taking a quarter of a quarter. Now 1 divided by 16, I'm using my calculator here. I think it's 0.0625. It is. It's 0.0625. 0.0625 means 6.25%. We've done a lot of percentages in the past, but that's the percent of the original screen that we see. Now that is a zoom in. we're not seeing 6.25% of, well, we're seeing it zoomed in. So we only see that percentage of what we saw to begin with. Okay, number 46. A population Y of coyotes in a national park triples every 20 years. The function y equals 15 times 3 to the x power represents the population, where x is the number of 20-year periods. So, okay, I won't interpret the 15 yet. They're probably going to ask me to interpret that in a moment. Now, based on this, I think the same thing is going to be involved when it comes to domain and range. Our domain starts at like x equals 0. Okay, that's my interpretation of this kind of question like this. Now 15 is the, well, we have to still talk about it. 15 is the y-intercept, and we're doing times 3. I feel like I have to change scale here, and I don't know by how much, given that that's 15. Why don't we just do it where this is 15 right here to start with? Like, boom, I got 15 right there. So 15, 30, I mean, all I'm going to do is triple values, right? But this is 15 to start. Tripling 15 is, boom, 45. I'll write down what these are here. So, boom, 45. Triple 45 is, boom, 135, which is basically up here, right? It's 3 up and then 9 up, things like that. I can kind of do it that way pretty easily. So, boom, 135. And then 9 tripled is, or 135 tripled is too far out of reach from what I want to do there at 405. It's too far out of reach. 15 divided by 3 would have been 5. Oh, there's the fly. Hold on. I don't know if you can see it on the... Where'd it go? I lost it. 15 divided by 3 would have been 5. But I don't know if our model begins that time before. I just saw the fly. I don't know if that model begins that time before. Then I'm going to start it at x equals 0 right here. So I'm just going to shift up like that each time. This is nonlinear, right? It's exponential. Just because I'm not drawing the other side with the asymptote. Actually, the asymptote doesn't really matter this time anymore. Because it's just a growth. Just a growth there. And there's my graph. It says describe the domain and range. To me, the domain is going to be greater than or equal to 0. This is when our model begins. Therefore, our population is at lowest 15, and it actually hits 15. So y is greater than or equal to 15 coyotes at that time. Keep in mind, x is going every 20 years. So when x is 1, that's 20 years later. B, find and interpret the y-intercept. So this is where we kind of hit this part. The y-intercept states that like when we start this thing, at the beginning of our tracking of this with the model or whatever, at the beginning of this model, there were 15 coyotes in the national park. So I don't know, that's not year 0. I mean, you can call it year 0, but it's not like 0 AD. It can be the year 2020. I mean, I don't know. Part C, how many coyotes are in the national park in 40 years? Now, this is one where you have to remember 40 years, X goes by 20-year increments. So this is 40 years later. This is 40 years later when X equals 2. That's not 2 decades later, 2 20-year increments later. So there are 135 coyotes. Let me type it. In 40 years, there will be 135 coyotes. Okay. All right. Let's keep going. Number 47 to 50. Write an exponential function represented by the table or graph. These will be easy enough when it comes to me representing y-intercept and growth or decay factor, given that they are exponential, which they clearly state that they are. So here's the thing. My y-intercept is the value of y when x equals 0. That'll be my a value. These are all y equals ab to the x, I assume. I don't see any sort of translations or anything like that. So this is my a value. And what we're multiplying by, they say it's exponential, so if this is times 7, then this must be as well. Times 7, this is my b value. So my equation will be y equals a times b to the x power. 2 times 7 to the x power. That's it. Pretty fast as an overall once you recognize what's happening and why this does what it does. That's why I avoid using a table. Or that's how I can avoid using a table. 48, by the way, I have to make sure x is increasing by 1 each time on that. Otherwise, it would change my thing, and it was. So, number 48. Now, number 48 is going to be a little bit different here as far as the conversation goes. For one, the fly was on my hand. I thought it was like a spider. For one, okay, x is increasing by 1. All right, the a value, I want to look at that in slow motion if I want. Yeah. The a value is negative 50. Now, you might indicate here that we're dividing by 5, and I don't disagree with you. You are dividing by 5. A times b to the x, though, says a times b to the x. What are you multiplying by? Dividing by 5 is the same as multiplying by 1/5. This will be stressed a lot more when we start talking about common ratios in geometric sequences. This is your b value right here, 1/5, not 5. Otherwise, that would be a growth, and this is a decay. So this equation is y equals negative 50. Oh, I don't want to graph that one. Negative 50 times 1/5 to the x power. Do not put times 5. Do not put divided by 5 to the x power. Exponential functions are represented through multiplication. Number 49 and 50 are graphs, but what are graphs other than some form of tables? I mean, heck, we've been skirting past tables to make graphs, so we might as well be able to do it here as well. If you notice, your a value is going to be the y-intercept, negative 0.5, and I'll gladly write the decimal. Now, if you don't know, as x increases by 1, you might not know negative 0.5 times what's negative 1, but we can know negative 1 times 2 is negative 2, times 2 is negative 4, so your b value is 2, and it's a positive 2. It won't be negative, it just keeps your values negative. So your equation is y equals negative 0.5, or negative 1/2, times 2 to the x power. Negative exponential growth with a y-intercept of negative 0.5. And then number 50, you have a y-intercept of 8. That'll be our a value on 50. And then your b value, once again, this is decay. We are dividing by 2 as we increase x by 1. Dividing by 2 is the same as multiplying by 1/2. So going from 8 to 4, I'll type it this way. I'm going to say 4 divided by 8, 2 over 4, or 1 over 2, which is literally 1/2. That's how they all reduce to. So a is 8, b is 1/2. This equation is y equals 8 times 1/2 to the x power. You can also write 8 times 0.5 to the x power. I'm going to leave them as fractions. Okay. Number 51. Oh, we've eclipsed 2 hours already. That's what's going to happen when you have a 40-minute lecture. Number 51. The graph represents the number y of visitors to a new art gallery after X months. Do we have to interpret anything yet? No. So in my interpretation is at the start of this, there were 40 visitors, and after a month, there are 60, etc. It says, write an exponential function that represents this situation. This is one of those ones where, again, we have the graph, but the a value is going to be 40, and the b value, I'm glad I just used the problem before, because 40 times what is 60? 60 times what is 90? 90 times what is 135? You might not know that number, so to find it, you divide a number by the one before it. That's how we determine that, right? 40 times b is 60. Divide both sides by 40, and that is b equals 60 over 40, or 90 over 60, or 135 over 90. The bottom line is they're all the same thing. Now, you can write them as one. You can use your calculator and do a decimal. You can do a fraction reduction. As a fraction reduction is 3/2. As a decimal, it's 1.5. So that's kind of up to how you want to write that. The exponential function to me is y equals 40. You know what? It's a word problem. I'll put 1.5. Although you can't have decimal numbers of guests, there might be some rounding involved. It says approximate the number of visitors after 5 months. So we have by month 3 there. You could multiply by 1.5 a couple more times, or you could substitute 5 into here. So 1.5, I'm just going to do this in my calculator. I'm going to do 40 times 1.5 raised to the 5th power, and that's just in parentheses like that. 303.75, you could say 304, like that. 304 visitors. And that's how I'm going to go about it here. Okay. Number 52. A sales report shows that 3,300 gas grills were purchased from a chain of hardware stores last year. That seems low. Oh, maybe a specific set of hardware stores. The store expects grill sales to increase 6% each year. About how many grills does the store expect to sell in year 6? Use an equation to justify your answer. So here's the thing. 3,300 gas grills can effectively be your A value. B is what you have to multiply by for it to increase by a certain amount. Now, you might remember this, but a 6% decimal equivalent is 0.06. But if we want to increase it, we would add 1 to that number. 1 plus 0.06, which is 1.06. If I want to increase something by 6%, I multiply it by 1.06. If I want to increase it over the course of time, I keep multiplying by it over and over, which is why we use an exponential function. Case in point, when we're looking at this one right here from the museum or whatever guest visitors there were here, 1.5 means a 50% increase. From 40 to 60 was a 50% increase. 60 to 90 was a 50% increase. We're going to do 6% increases here, so 3,300 times 1.06 to the x power. Y is the number of gas grills. X is the number of years. So 6 years, it says in year 6. This is last year. So in year 6, we substitute 6 into here to the 6th power, okay? So that's what we're going to get here. And I don't believe we had to graph this or anything like that. So I'm going to use the calculator for that one. 3,300, and I'm going to round to the nearest whole number, times 1.06 to the 6th power. It's going to be a crazy decimal. 4681. 4681 gas grills in year 6, okay? Sold in year 6. That's the expectation, that if we increase by 6% each year. You can say that about money, you can say that about a bunch of different things, and that's what I'm going to state with that one. Number 53. Graph the function f of x equals negative 2 to the x power. Then graph g of x equals negative 2 to the x minus 3. How are the y-intercept, domain, and range affected by the translation? Well, now we have to graph both. But I'll probably just copy and paste one into the other, because that's literally what these things are. That's actually, well, that's not how I would graph it. That's how they'd graph it. But f of x equals negative 2 to the x power. Let's get that one started. This has horizontal asymptote here. Negative, see, the 2 is not negative. You have to remember that. It's the 1 is negative multiplied by a 2. So a negative 1 is here, and then there's a doubling effect going on. Times 2, times 2, times 2 is 8, times 2 is 16, all down from the asymptote there. And then divided by 2 going this way. 1/2, 1/4, 1/16, etc. So there's this graph. The next graph is this minus 3, which means everything becomes 3 lower than it was before. You know what? I won't copy and paste it. I'll just use it as it is. So g of x, let me do one thing though, because it's negative. Let's move it up here. All right, g of x is negative 2 to the x power minus 3, right? That's the difference. So this horizontal asymptote, and I have to use a different color probably. This horizontal asymptote is negative 3, and everything is as it was before, just from here instead. So a negative 1, kind of y-intercept if you will, and then times 2, so 2 down, 4 down, 8 down, 5, 6, 7, 8, and then 16 down, which probably can't fit in comparison, but I'll pretend like it could. 1, 2, 3. Everything's 3 lower than it was before, right? And that's why copying and pasting would have been quite okay in that situation. So same graph, translated 3 units down. So there are the 2 graphs there. Those are actually pretty good looking, all told. Now, they don't mention asymptote, right? They haven't ever come up with that phrase for us yet. Okay, so how are the y-intercept, domain, and range affected by the translation? The y-intercept and range are 3 less than they were before. The y-intercept instead of negative 1 is negative 4. The range instead of y is less than 0 is y is less than negative 3. The domain is unchanged. It will largely be unchanged for these. Even if I horizontally translated it, the domain's unchanged. The x's are still between, this and that for the whole thing. So, again, range, shoot, I should probably write these. So y-intercept is at 0, negative 1. Range is at y is less than 0. Listen, domain's all real numbers. I'm not even going to write it. Y-intercept here is at 0, negative 4. Range is y is less than negative 3. And there's a difference there. Okay, number 54, making an argument. Your friend says that the table represents an exponential function because y is multiplied by a constant factor. Is your friend correct? Explain. Well, what your friend fails to recognize is that the x values are not increasing by a constant amount. It increases by +1, +2, and +3. So my friend is incorrect. My friend is incorrect because the x's are not increasing by a constant amount. And I'll just write the +1, +2, +3. If it was +1, +1, +1, or +2, +2, whatever, like that, that's fine. Therefore, it's not exponential. I don't know what it is. It's not exponential. There's a pattern. Doesn't make it exponential. Number 55, writing. Describe the effect of a on the graph of y equals a times 2 to the x when a is positive and when a is negative. Well, I don't know if they're asking us to do when a is more than 1 and between 0 and 1. I'll just say that when it's positive, it's going to be at some stretch or shrink. When a is positive, there is a vertical stretch or shrink, but no reflection over the x-axis. When a is negative, there is a reflection in the x-axis on top of some possible vertical stretch or shrink. See, they never said that a can't be 1 or -1. To my knowledge, I don't believe there's anything I wanted to say there, but I just want to italicize a. Otherwise, it just looks like any other article instead of a variable. Okay, so that's I'm going to say number 55. Number 56, open-ended. Write a function whose graph is a horizontal translation of the graph of h of x equals 4 to the x power. Horizontal translation is where we're changing, the thing inside the exponent. So like this is h of x equals 4 to the x power. Translation of this g of x would be like 4 to the x minus 3 power, something like that. This is translated 3 units right, which is a horizontal translation. That's it. Okay. Number 57. Using structure. The graph of g is a translation 4 units up and 3 units right of the graph of f of x equals 5 to the x power. Write an equation for g. These questions are nice and quick. We don't have to graph. So f of x equals 5 to the x power. Now, notice that they're going to mention a g of x with a 4 units up. That's a k value of 4 and 3 units right. I just did that for this one. That's an h value of 3, and we got to subtract the 3. So 5 to the x minus 3 power plus 4. Nice and quick. Oh, Mr. Fly. Number 58, how do you see it? The exponential function, I don't want to see the fly. The exponential function y equals v to the x power represents the projected value of a stock x weeks after a corporation loses an important legal battle. The graph of the function is shown. This is all too real. So it's losing value, losing value. After how many weeks will the stock be worth $20? So we find where $20 is for y, and we say that that's 2 weeks later. That's how I see this. After 2 weeks. Part B. Describe the change in the stock price from week 1 to week 3. So week 1 was at $40, week 3 is at $10. So I can state that over week 1 to week 3, the price dropped $30. Now, that doesn't explain, see, that's just a difference. It doesn't explain the percentage difference. What I'm seeing as a percentage loss is every week it's losing half its value. It's losing 50%. So I'm not describing it that way. I'm just saying the difference. It just says compare them from those two values, and comparison's a difference. All right, number 59. Using graphs. The graph represents the exponential function f, find f of 7. Now, if I had the graph and I could find 7 and find the point there, I'd just say, hey, there's the y value, and I'd plot it, right? F of 7 means the value of y when x equals 7. However, we don't see that point. So what we probably have to do is come up with an equation, some f of x here. It's going to be based on our a value, and I'm going to determine the a value is negative 1.5. It's the y-intercept. And what b is the growth factor over that time. We go from negative 1.5 to 3. Even if you didn't know what that was, negative 3 to negative 6 is times 2. So this is times 2, times 2, times 2. That's our b value, 2 to the x power. So f of 7, I just got to substitute 7 into that one, and voila, that gets my answer. Now, I can probably do that without a calculator. 2 times 7 is 128. Half of 120 is 64. I need that because I need to add 64 to 128, which is 192, and make it negative. I believe f of 7 is negative 192. That's what I'm going to go with. I fully believe my own mind on that one. Number 60, thought-provoking. Write a function of the form y equals ab to the x that represents a real-life population. Explain the meaning of each of the constants a and b in the real-life context. So you saw that one that was like the gas grills one. Populations might not double over time very fast. It might have a slow trickling of something like that. I'll state something like, you know, what, like, okay, I'm going to like make a word problem out of this. Like the city of, actually, let's come up with what, I'm not going to use real-life numbers. The city of Happyville is so happy that currently has how about the town? The town of Happyville currently has a population of 2,000 people and is increasing at a rate of 3% every year. There's a situation. So A represents the number of people initially, the currently thing. So that's A. 3% increase is 1.03 like that. I mean, that's kind of as best as I'm going to be doing it with that. There are different things you can say, but that's the kind of population I'm going to do there. We could do a bacteria population, right? They did a bacteria one earlier. I'm just going to do a small one like that. All right, number 61. Got 3 more questions to go. At least we'll hit probably under 2.5 hours. Let f of x equals ab to the x. Show that when x is increased by a constant k, the quotient f of x plus k is always over f of x is always the same regardless of the value of x. So if I do f of x equals ab to the x, that means f of x plus k, remember you'd have to substitute x plus k in for x, that's a times b to the x plus k power. Now, were you guys, I don't think you guys, I think that was IM3 that did, yeah, you guys didn't do these. When I do f of x plus k over f of x, that's the same thing as doing a times b to the x plus k power over a times b to the x power. Now, because these are multiplied, I can do this a divided by a and get 1. Those are good. The b's, however, cannot because order of operations takes over. Now, here's the part where you'd have to know how these exponential properties work, but a sum of exponents means keeping the base with 2 different exponents right here, b to the x times b to the k, and this is all divided by b to the x power, so I can separate it that way to really work it out. Now, b to the x over b to the x can become 1, and you're left with b to the k power. B is a constant. K is a constant, like those are actual numbers. So they're saying it's always the same regardless of the value of x. This is a constant amount here. So when you do that, it's always the same b to the k amount regardless of what you do. Okay, that's how I'm going to go about talking about that. Okay, number 62. A function g models a relationship in which the dependent variable is multiplied by 4. For every 2 units, the independent variable increases. The value of the function at 0 is 5. Write an equation that represents the function. This one's a little bit different because it says it quadruples every 2 units, so you need to think of what it does every 1 unit in that case. So for one thing, our a value can be 5, which is good. Now the b value is not 4 because it's 4 for every 2 units. There's more than one way you can represent this. One's a little trickier than the other. The way that we're going to do this for now is just y equals a times. And think about this. When we have, I mean, we could graph it, right? We could come up with, it starts at 5, and then at 2 here, it's at 20. So it's at 5, and then at 20 because it quadruples. Well, what did it do in between there? You did 5 times some b times another b, and you got 20. You divide by 5, you get 4, and you take the square root. You would actually get plus or minus 2, but in this case, b can only be 2. You get 2 there. That's one way of working that out. Probably the better way of doing it. You could also guess and check. If you quadruple every 2 units, then you must be doubling every 1 unit. That's at least an idea anyway. So there's that. Another idea, and I don't think it's worth coming up with you guys here, something you'd learn with half-lives. I'm probably not going to do it because you'd have to know what rational functions, rational exponents are. And yeah, you guys didn't do that. So I'm going to leave it at that one. That looks pretty good. But 5 times 2 to the x power. That way in between when x is 1, y is 10. And then you double the 10, you get 20, and boom, you hit that. All right, number 63 is the last question. It says, write an exponential function f so that the slope from the point from 0, f of 0, to the point 2, f of 2 is equal to 12. Okay, so we have a 0, f of 0, and 2, f of 2. What we're saying is we need our slope to be y2 minus y1 over x2 minus x1 to be 12, or f of 2 minus f of 0 over 2 to be 12, or if you multiply both sides by 2, f of 2 minus f of 0 needs to be 6. So that, sorry, 24. Multiply by 2, 24. So we need the difference between this value and this value to be 24. You just saw from the previous question what it means to go, well, this is kind of open-ended here, so I can kind of pick and choose what I want. If I have a difference of 24 between two values that are that many points away, then I need to be I can make my f of 0 be I'm trying to do this in an algebraic manner instead of a guess and check. And I don't know if the algebraic manner is something you guys would be ready for here. But my f of 0 needs to be something so that I'm 24 farther out the next time. Let's do times. See, I'm not very good at differences with these. I'm good at ratios, but not differences. What would work? If I did 4, if I had 4 as my y-intercept, 24 away from that would be 28. I don't want to multiply that. If I did 3 as my y-intercept, 24 would be 27. Let's do that. We can do 3. I can do, I believe the equation could be f of x equals 3 times 3 to the x power. If I do that, I have an x-intercept. This was kind of guess and check, but I have an x-intercept, a y-intercept, excuse me, of 3. When x is 1, we triple that and we get 9. 9. And then when x is 2, we triple that again and we get 27. 27 minus 3 is 24. So that difference is 24. That's a slope of 12 in between those two things. That's what we're looking for there. So f of x equals 3 times 3 to the x would work. Let me think of another one. 6 plus 24 is 30. I don't want to get an easy one there. 7. Odd numbers, well, I did an odd number last time. 7 plus 24 is 31. No, 8 plus 24 is 32. 8, we could times 4. We could double 8. You could do 8 times 2 to the x power, because f of 0 would be 8 and f of 2 would be 32. And 32 minus 8 is also 24. So here's another one. So there are a couple right there that we can use. Maybe there's some negative, well, no, not negative versions, because then the slope wouldn't be positive, but that'll work there. I guess you can do some negative decay ones, but that's it. All right, guys. And that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Probably the longest video that we've had, or maybe that we will have. It depends on what we have to do for geometry and proofs a couple chapters down the line. But very long lecture portion, but I hope that everything consolidated itself into such a way that you can learn some tableless form of graphing. So I don't know if we're going to do much tableless graphing in this chapter beyond this section. Obviously in chapter reviews and things like that, but if this is my one place to hit it, I'm going to do it here. I have a bunch of other videos where I do tableless exponential graphing. That it's not just for IM1 videos though, but if you look at graphing exponential functions in Mr. Robinson's virtual math classroom, you're going to find some videos for that for sure. And I mentioned the same thing over and over. I don't like using a table. I have no reason to in these situations when I can just multiply or whatever, divide each time that I have it. So thank you so much for watching. Take care. I'm going to see you in the next one.